I have like obviously read bits of it. Actually, sorry, Rajan, how are you?
Okay. So sorry, I couldn't. I had some internet thing. I had to reboot the computer, things like that. When did you start? When did you start?
It looks like you just started the live stream there.
Yeah.
Well, I got in here around 22, maybe quarter past, or sorry, quarter to, something like that. So
8:40. About 15 minutes ago.
Yeah, right. Or well, no, more like 20 minutes ago.
Oh, and then Gerd was there.
Gerd was already here. So we've been discussing his just going into more of the finer points on his theory.
Oh, so it is not recorded what you discussed.
We didn't record any of that. We were kind of waiting on you.
Oh, thank you.
I mean,
yeah, so we had to start over then, kind of. I mean, if you want to record something. So was it a brief discussion or just a side discussion or part of the, mainstream?
I was kind of looking for more definitions, really. I asked him initially what a line element was in his theory, if it was equivalent to a mathematical line element. And Gerd, you explained that it is actually it's actually an object, like a physical object, as opposed to a mathematical object. And that is the metric crystal lattice that he has is a line element. So that kind of clears that up in a sense. And then I was talking about degrees of freedom within cosmological models and quantum field theory. They talk about how many particles in the universe. So it might be what did I say, 10 to the power of 90.
Yeah.
And then when you talk about different, like other dark energy and stuff, then there's a lot way more. There's like 10 to the, I don't know, is it 238 or something? So they talk about the degrees are higher for dark energy and black holes and stuff, whereas for matter it's a lot smaller because there's way more of this dark energy and dark matter than there is normal matter. So I was kind of interested in that because when you hear about degrees of freedom in physics, certainly in particle physics, you think of like the degrees of rotation that are allowed for spin, let's say, or some other kind of gauge theory. But then when cosmologists seem to be talking about degrees of freedom, like Gerd and other cosmologists, talking about exponents, like the degree to which how much matter there is. So I was asking Gerd maybe to clarify that, or if he knows what I'm talking about, like the distinction I'm trying to make. I mean, Gerd, you're on mute there. I don't know. Did you follow that, Gerd? Oh, Gerd is.
Oh, Gerd is switched off his mic.
Yeah.
Hello, Gerd.
He might be watching a video or something.
Yeah, now he recognizes.
Okay.
Something about.
Yeah.
But I did not understand what you asked me.
Yes, that's okay. So was there any part of it? So really what I'm asking is in cosmology, when they talk about degrees of freedom, like in your field, essentially, where we're talking about all of, the big stuff, space and different types of matter, when they say like degrees of freedom, and then they're talking about a very large number with a large exponent to classify maybe all of dark matter and dark energy and black holes.
Oh, no. In my model, there is dark energy. You can name the metric wave field as dark energy because its temperature is 0 Kelvin, but there is no dark matter.
Okay. So that's interesting. Well, like in your model, when the universe begins to expand, yes, the number of line elements increases.
I calculated the number of line elements and of bosons and of in my book, yes, somewhere. Shall I have a look where?
Yeah, you can. That's no problem.
But it may be take some time.
That's okay. Yeah, but you can always use Control F or however you do it. So, well, the other issue is as it expands, the degrees of freedom also increase. Correct?
Yes, but the number of line elements is increasing with expansion because the wave field not only expands, it also propagates at the edge.
Well, what's the difference between what's the difference? Oh, because expansion would be lateral, kind of along.
The expansion is when the
propagation
wavelength is increasing. The wavelength of the line elements between the observer and the end of the at the edge, and propagation is because it's an electromagnetic field, and at the edge the propagation speed is about 0.9 the light speed, and that means that it is also propagating, which increases the number of line elements, the total number of line elements.
Right. Because if it's propagating, if the edge is propagating, it's moving out. Yes.
Yes.
Isn't that equivalent to expansion? Because it is. So why make a difference between the speed of expansion and the speed of propagation?
There are because with only expansion you cannot get light speed expanding universe. You need also the propagation.
Oh, okay. So without, right, but I kind of get that you said that, but I'm just curious, wouldn't expansion and propagation be an equivalent thing? Because let's say I have a balloon and I expand the balloon.
No, not that's aren't equivalent things, because the values are different, and the expansion is also abhängig. It also depends from the distance of from the observer. The farther away, the more the faster the expansion is.
Yeah. Okay.
Because the expansion was the expansion rate was greater earlier. Yes.
Well, that's one explanation. I haven't heard that one before. That's a pretty good one, though. But as far as I know, the reason that they state why things are traveling faster the further away they are from us is because of like a compound effect. Like each point in space is expanding the same amount, but when you look through the distance of all those expanding spaces, you have to like accumulate all those expansions, and then gradually that becomes like a compound effect. So something further away is moving, it's twice as far away, there's twice as much space in between, and that grows twice as much, kind of thing, as something that's
I exactly calculated the expansion rate as a function of distance. That's
I also have one question.
One moment.
Yeah, absolutely, Rajan. Jump in whenever you want to.
Yeah, I think after recalculation, one thing I have to Gerd is that you are talking about a stretching of the light itself. Are you talking about a stretching of light? That's what.
Yeah, that's interesting, Rajan, because we were discussing that before you came in. So.
Oh, okay.
Yeah, I asked the question I was asking Along those lines, something that I heard about, that as the space is expanding, the light is stretching, but you know, the frequency isn't changing, obviously, because the speed of light is constant. But then we were also getting into the point that actually, I think Gerd made the point that the frequency and the wavelength are ratios, that if one changes, the other one has to change in order for the speed of light to be constant.
Yeah.
No,
So
the speed
up because of the expansion of the universe. Is that correct, Gerd? Does that sound right to you, Rajan? That's
light speed is only a constant with respect to the subspace.
Yes.
And if the expanding or if the propagation speed changes of the metric wave field, light speed with respect to the observer, which is traveling with the metric wave field, changes too.
Right.
But because the propagation speed of the metric wave field is such microscopic, you cannot measure the difference in the lab.
Right. Yes. Okay, that makes sense. That was another point that we discussed before you arrived, Rajan, was Gerd's concept of you mentioned the subspace and then the speed of light. I'm just trying to remember how exactly you formulated it. It was something to do with but essentially, there was the propagation of the subspace is very, very small, but it was greater.
No, the subspace doesn't propagate. The metric wave field propagates inside the subspace.
Okay.
And the subspace, because of its basic properties, which is the light speed is defined as a constant value because of mu 0 and epsilon 0.
Right. Yeah.
But it's mu 0 and epsilon 0 are properties of the subspace. Thus, light speed with respect to the subspace is a constant speed, but only with respect to the subspace.
Yes.
Okay.
But we aren't in the subspace. We are in the metric wave field. We are living in the metric wave field.
So is the universe then the metric wave field, or like the place we inhabit now? Would we call that the metric wave field, or is that the subspace? I'm getting a bit confused. Sorry. Or are we something? Or is this something else? Is this a different?
The metric wave field is a lattice, yes, but of Planck length. Yeah.
But wait a second. So there's so the lattice is very small, and so the lattice is not the subspace. They're two different things.
No, it's not.
That's interesting.
Lattice is in the subspace.
Right. So the lattice is not the metric. The metric is the subspace. Yeah.
No, the lattice is the metric.
Sorry, what?
The metric is the subspace. Is the lattice. The lattice is the metric. If the Planck length is increasing, all things within are increasing too. All matter.
Wait a second. A subspace has a metric, does it not? It is a coordinate.
No, subspace has no metric.
But then what does it have? Is it a coordinate system?
Subspace is like a plenum, yes, or it's the space electromagnetic waves are propagating in. Normally, photons could propagate also in the subspace, but because of the very great specific conductivity, the wave would be finished after 1 or 2 periods.
Okay. Yes.
Because it's a situation below the aperiodic borderline case.
Okay. So
there's no,
So one of the things.
But the metric wave field is able to propagate without lossless.
Yeah. Okay. So Rajan, you had a question there.
So one of the things in the perspective. So if both to Gerd and Christopher together, I mean, what I'm trying to see is the perspective of the multi-phase. We are talking about superluminar with Emmanouil also, superluminar, vacuum, and subluminar. So according to Gerd's thing, the subspace will be like vacuum. I think.
The superluminar is only possible at
maybe
at the level of the Planck length, but it's the same as in this movie from YouTube of Emmanouil, which Emmanouil posted some minutes before.
Yeah.
And
I have not looked at it, but the thing is that so let me put it in a perspective, and Gerd, Christopher, you can correct me if I'm wrong. One of the things is the subspace will be like the vacuum which holds the speed of light constant, and the metric field will be the subluminar level that we are living in. Will that be correct? So
the problem is if metric wave field. If there would be no metric wave field, superluminar speed would be possible without problems. But
so that's what. So one of the things is that the vacuum can fluctuate. I mean, the phase of the vacuum can fluctuate. So it can stretch the light. I mean, there's a possibility, like you are superluminar. Let's say superluminar is up there.
Yeah, but superluminar not for photons, for bosons would be possible.
Yeah, but superluminar, there is no form. There is no structure. There is no form. Everything is kind of chaotic, just moving around. Only like monopoles will be there, things like that. There won't be any light or sound or even space or time. No, I talked about a sense. There may be a field, kind of a field.
But I think there is no superluminar speed possible, but instantaneous speed. Not superluminar, instantaneous, but instantaneous. Wechselwirkung. Interdependence or instantaneous interdependence is also possible when the metric wave field exists, but only in some special cases.
Do you mean entanglement? That kind of
for observers which are located at the 4D hypersurface, like the event horizon. The interesting thing is somebody means we aren't at the event horizon. Yes, we live at the event horizon because there is no space after the event horizon. The event horizon is not a space, it's a time. And time after we are living is in the future, and the future not yet exists. But so we are living.
I will come after a while.
Yes, yeah. But it's not the only one event horizon. Maybe at the black hole there is another event horizon.
Yes, you were saying. I wonder though about that, because you seem to have like slightly different terminology on that to maybe the rest of, would you say, standard cosmology? So with there you have the particle horizon is the observable universe.
Yeah, the particle horizon is also a 4D hypersurface seen from the observer. But if you would be there, it's only a point, and you cannot matter cannot overcome this border. Yes.
Oh yeah, yeah. Okay, that makes sense. I think that's very similar to what I'm working on, but a little bit different as well. Or is it? I'd have to think about that, but yeah, it sounds fairly similar to what I'm talking about. But then in standard cosmology, what I'm trying to get across is that they have the particle horizon, which is merely the boundary of the visible universe, yeah? Is it? And then the event horizon is due to the expansion of the universe. It's the point at which like no more information can come back.
No, the particle horizon is the expansion center. And the event horizon we are living at is the event horizon of the whole universe, and it's a 4D hypersurface and all. But it at the time of the Big Bang, it was all was at the same point. And thus, all people are living at the event horizon of the 4D hypersurface are connected with instantaneous connection. Maybe, yes. They are all at living at the same point.
Yes, understood.
In time, not in space.
Yeah.
But, and event horizon outside.
Wait a second there. What does that mean? The same point? Oh yeah, same point in time. It's like yeah, I see what you mean. Yeah, like non-relativistic.
Yeah,
time.
but instantaneously is in time, not in space. Yeah. And an event horizon outside a black hole means that inside is an event, not an event horizon, but a particle horizon. Event horizon outside is a particle horizon inside, because no matter can leave the black hole, because it's abgestoßen.
Infinitely dense or something.
Moment. It's repulsed by the particle horizon.
Oh, you mean it tries to get out, then it's sent back in?
Yes. The particle horizon is an expansion center, which repels all matter outside. Yes.
Okay.
And if you try to overcome the the particle horizon, it's impossible. Yes.
Yeah. So when you're talking about an expansion center, though, this is a quick question for you. I'd say, the way when we talk about space expanding, they say it's expanding from all points, like space is expanding everywhere. So wouldn't that mean
but it's not 3D dimensional, it's 4-dimensional, yes, with hypersurfaces.
Okay, but what I'm trying to get at is that let's say everything's expanding, so then there's no central point of expansion, and wouldn't all points be the particle horizon in the universe?
Seen from us, the particle horizon is also a 4-dimensional hypersurface. It's at the world radius, and it's outside, seen from an observer living at the event horizon. Yes.
Right. So by the sense of it, the particle horizon and the event horizon are the same thing, seen from different sides.
Yes.
Okay, that is pretty interesting. I'm just gonna
and the whole universe is expanding exactly with light speed.
Okay.
Expanding plus propagating, and I have there also an interesting. No, but I cannot find it yet now. An interesting graphic where
I had to attend to something. Some people are, so things are going on at home. So that's right.
Okay.
So what you are talking about, the subspace and the metric field, metric space?
We kind of moved on to the particle horizon and event horizons. I'm not sure how we got here, but
yeah. So one of the things I explained, like multi-phase, like let's say this is superluminar, then you have the vacuum which holds the speed of light constant. Then you have subluminar phase where we are. Now I would think that Gerd's metric space is in that subspace. Is it called a metric field or metric space? Metric field, right? Gerd calls it metric field.
There's the metric waveform. There's a lattice as well, which is kind of.
It has a special time function which I got with the solution of a special differential equation of the model with expansion. That's all in my book. You can read.
No, I do. Yeah, I like that concept, and I think Rajan, you picked up on it early on about the event horizon and the particle horizon, and that like the event horizon of the universe is like, if you were to go beyond it, I'm assuming you're just back in the universe, but at a infinitesimally a point in the future that is just like 1 second in the future or 1 millisecond in the future or something.
Yeah. So one of the things I find from I have published papers, and few of the papers are the peer reviewed. I have put about how the space, time, and the sense work together. The sense gives the field effect. So from the
I don't know.
You must see our universe is like a black hole inside, yes, and the particle horizon is that point or surface or hypersurface which propagates with the highest velocity, such while the event horizon is nearly static. Yes.
So how are they the same thing if they're moving at different speeds?
So from seen from like, an observer.
If this, yeah, okay, right. You're going to explain there. Go ahead, Gerd. Sorry. Sorry, I was just going to ask. You know, if this is seen from this side, this is the event horizon. Seen from the other side, it's the boundary. So how, if they're the same thing, can one be moving at an infinite speed and the other one be static?
But I cannot say if it is seen from the other side is the same of the same universe or of an other universe. I cannot say. Yes.
So that's multiverse. You believe in multiverse. You're talking about multiverse.
He's saying he doesn't know. So it could be the same universe on the other side.
If it is the same, then the event horizon and the particle horizon would be connected together. But if it is another world outside, then not. Yes.
So what you're talking about, let's say it's a black hole here. So the universe, our universe is in a black hole. So the black hole has event horizon, right? Then the particle is inside that black hole, and the particle itself has a horizon. That's particular. Is that what you're saying?
Yes, but if they are connected together, you must see like a horseshoe magnet. Yes, the North Pole is the event horizon, and the South Pole is the particle horizon.
So you're talking about the magnetic like monopoles, north and the south. So you have the particle horizon. That's a North Pole has its own horizon, right? It may have its own horizon. South Pole may have its own horizon.
But I cannot answer this question because is it the same universe or not? I cannot say. Maybe that outside our universe is another universe, and we are living only in a black hole.
Yes.
So in terms of the superluminal thing, so we have to be in the subluminar level, I think, because, the speed, maximum speed of light, speed that we can achieve, speed of light in the subluminar level. So we are living in the subluminar phase.
I can show you the figure with the expansion and propagation velocities, but you can in my electrons it's figure 32 at page 61, but in the metric universe it's also, but I don't know where. I cannot find so here. It's figure 44b at page 79.
Can you put it up? Can you put it in the screen?
It's a metric universe.
Can you put it in the screen? Can you put the present?
Yes, I can.
Thank you.
You see? Do you see?
Not yet. Yeah, now I can see. Yeah, we can see. think Christopher also. Oh yeah, this is, you are saying that, okay, the observer, and you have the propagation and null vector. What is the null vector? Null vector.
One moment.
So where is the subspace? Where is the metric space?
Here you have the propagation share of the metric wave field, and that's the expansion share of the whole universe. And but it's curved, as you see. And if you take this the length of this, then you get the space-like vector, and the result is the zero vector, and yes, and it is expanding with light speed, but only expand. But if you want to go at this vector, you have to change your course always, because it's like a great circle distance. Yes.
So that keeps the speed of the null vector, keeps the speed of light constant, right?
Yes, that's with respect to the subspace.
So that's the subspace.
And it's the expansion of the whole universe. That's here's the observer, and here's the edge of the world. Yes, the particle horizon.
So where is the particle horizon? Where is the?
But the particle horizon propagates in this direction with a curved vector. Yes.
Oh, the phi vector.
No. This is the propagation, and this is the expansion. Yes, the expansion share. Yeah. The expansion
is on the horizon is in the expansion share. Particle horizon is in the expansion share.
Here, that's the 4D, four-dimensional hypersurface. So it's the blue line here.
Okay. So that's the particle horizon.
The particle, yes, that's the particle horizon.
So the particle horizon be further than the.
But if you want, if you really would be at this point, it would only be a point, and you would see the observer at four-dimensional hypersurface, the event horizon.
So can particle horizon go further than the?
But you cannot go to the particle horizon because you are. Can I stop the?
Yeah, I'll do that.
So.
Yeah. Okay. So you are saying the particle horizon, can the particle horizon go further than the event horizon for a black hole? No. Or it has to be inside the event horizon or black hole. Particle horizon and the black hole. If you compare the particle and the black hole, can the particle horizon go further than the event horizon or the black hole? You know
what is a black ball?
No, suppose we are inside a black hole, the whole universe.
Black ball.
Oh, black
hole.
Singularity. Collapsing star.
The whole university is the whole universe is a singularity.
Okay, so that's inside. Can the particle horizon is inside? Can it go outside? Can it go outside?
No, it's a particle horizon. You cannot go outside. Maybe if you. But I cannot say if it's correct. If you are made from antimatter, maybe that you can go outside the universe. But the last or the latest experiments with antimatter seems to be that antimatter is also angezogen.
Restricted.
Is also attracted by normal matter. Yes.
Oh, interesting.
Then it should be or shouldn't be possible to leave our universe.
Okay, yeah. So I think the question.
Dark matter. How about the dark matter? Can it go outside?
Oh, dark matter doesn't exist. Only dark energy.
Dark energy. Can it go outside? Will be outside the black hole?
Because the dark energy is a metric wave field. It cannot go outside because it defines outside. If it propagates and expands, yes, I cannot say, but I think the whole universe is a black ball.
A black hole, yeah.
I say black box.
Hole, yeah.
See, I say from a transform, the whole universe is a black box. So it does make sense. So a specific case of the black box will be black hole. So
yeah, I don't understand what a black. Do you mean a black ball, a black hole, a blackboard?
Yeah, black box. So that my transform, when I did the whole general transform,
please spell the word ball.
BLACK, black, then BOX, box. Like
box. Black box. Yes, from outside it's a black box.
Yeah.
It's like a black hole. We don't know what is inside.
Yeah, I think Rajan's original question, though, seemed to be specifically about black holes. So the collapsed star singularity.
Yeah.
And I think you were. What was your question, Rajan? It was about the particle horizon of the black hole and event horizon of the black hole, and you were wondering if they were propagating at the same speed, or
can it go outside?
Yes. All all black holes are expanding. That's what somebody has calculated that the black hole doesn't shrink anyway. Yes.
In our universe, like from our perspective, they're expanding.
Yes. I can, if I have a look, I could say what's why? Moment.
I suppose they're gaining matter, aren't they? But then, aren't they?
Moment. So gravity is the maximum. It's maximized. So now anti-gravity is working.
Seems to be something.
The graviton and Emmanouil's graviton thing.
We've been going for an hour now.
And the universe is a rotating universe, yes? It's
we may have to stop another 10-15 minutes.
Well, I was thinking about a break, but do you have to do something, Rajan?
Yeah, somebody may be coming after 10, but I'll find out. I mean, we can continue, or if you want to take a break now, it's fine. We'll come back after 5 minutes. 5 minutes or
so well, maybe 10 minutes. But Gerd, did you say that the universe is rotating? What's it rotating around? Is it a 4-dimensional point? It's a hypersphere, or I think you're looking up something. So give me a minute.
Now, with respect to the black hole, I would prefer. I would recommend section 4.6, energy and entropy of my metric universe. There's all something is written down. Yes.
Yeah. Okay, we'll check that out. But would that cover the I was just asking about, you said the universe is rotating.
Yes.
Well, what's the point it's rotating around? 4-dimensional. All right.
It's rotating and expanding and propagating, and the rotation is on each possible axis.
All right, and so is the rotation equivalent to the speed of light?
Yeah, but interestingly enough, the rotation is always, because of the expansion and propagation, is always one turn outside.
So you're saying that? Hang on a sec. So the propagation, expansion. How do you mean it's one turn? Sorry, I don't understand. So as it expands and it turns once.
Yeah, and because it expands more and more, it must rotate more and more, but it doesn't exceed one rotation, one turn.
Ever? Well,
yes.
It's like a spiral, is it?
Yes,
but like a vortex. I was thinking the same thing. Vortex.
But wait a second, a spiral does go around, so it can't.
Yes, but I have a good one moment.
Like as I was saying, a spiral can do more than one rotation.
I can show you like it takes place. Here, yes.
It's in between.
One moment. That's the track of a light. The green is the track of a light ray which has been from the Big Bang to the observer at the normal today or nowadays. Yes. Mm-hmm. And there are the rotations in all axes are berücksichtigt. Are considered, yes.
Oh, is that what's OR sub capital OR?
The green ray is that of a light ray, yes, and that is that from the red one is that from gravitational.
Graviton?
No.
Entropy.
No, that's
gravitation field.
It's a distance between the observer and
particle
body. It's a constant wave count vector.
Oh, okay. So what's the yellow one?
The distant. The yellow is zero. No, it's a great circle distance.
Oh, right. So that's the speed of light.
You have to change the course every time. But it's a two-dimensional projection, and Yes, and as you see, there's only one rotation.
So do we have the light coming out from the Big Bang and then coming back to the what do you call it? The event.
The light does not leave our universe. Yes.
Right.
And because of the curvature, the length of a light ray may be greater than CT. It may be up to 2 as the double distance.
Okay.
That's why we have we haven't a dust universe. We have radiation universe, and at the radiation universe, the Hubble parameter is always 1 divided by 2, divided by twice the age. Yes, that's why you have here.
Oh yes, or oh yes, he's kind of.
Okay, it's not the age is double. T is more not the age. It's time constant of the differential equation, and here is also one-dimensional difference. And as you see, you can a particle which is the distance. If you pass the particle horizons, you cannot catch it. But if you can pass it, then the distance to the observer would be decrease again. Yes. So
okay.
I will stop. So,
very good. Okay, I think we'll take a break there.
Yeah.
And Rajan, you can check how you're fixed for time if you.
Yeah, I think I can. I mean, we can come back, but I may have to stop another 5-10 minutes. So I don't know. I mean, the person is coming in about 20 minutes. So, and I may have to be with them. If you want to continue, is fine. But I don't know how long that will take. Maybe another 10 to 15 minutes.
Oh, right. I see. So you prefer maybe to take the break then, is it?
Yeah. So we can.
Well,
we can continue another 5-10 minutes, but we may have to take a break about half an hour. I don't know.
Oh, but I think I will watch the movie from Emmanouil to the end in this break.
Okay.
Okay. So you want to come back after half an hour?
I would stop with my explanations, and if you have another subject to speak about or to talk about.
Yes, I suppose we could think about that, because there's quite a bit to digest there. It's pretty interesting theory, though, Gerd. I like it. It's kind of mystical almost, but obviously there's a lot of quantization in there, so that's good. Yeah, I think we will take a short break then, 10-15 minutes, and then we'll come back maybe with some other discussion points. And
you want to play Emmanouil's video in the presentation? You want to put it in the presentation?
Yeah, but you can play it originally, because he sent the link to it.
You're saying
we can play it. We can play it in this one while we are taking break.
Yeah. Maybe. Let me see if I can do that.
And then, so we have enough time. How much time is that? Half an hour? What is this?
No, no. He sent
Like minutes.
started within the video. It's not the whole video, but after 4,830 seconds from the start. It's about 3 minutes.
Oh, that's it.
The rest is about 3 minutes.
Is it a Nobel laureate? Nobel laureate guy? Oh yeah, Nobel laureate, right? Oof.
Particular standard model, this is true. So for all the standard model interactions, no interaction can ever send the
Well, can you hear that?
This is effective.
I cannot really hear much.
I don't know.
Increase the volume.
Oh, do I? Okay.
The professor is speaking very fast. And
you have either spin 0, spin 1/2, and spin 1. Other spins are not possible unless you find a locative some sort. So spin 2 would be forbidden, but the graviton is spin 2. So now does the graviton
is the CC there? Closed caption?
Can
you put
yes, in another tab I have I already opened this video.
But when you reach Planck scale, all of physics has to be rephrased. So there, locality closer to Planck scale is probably not possible. I would expect that space and time become a sort of
oh, something happened to the audio. Anyway, I'll come back after 10 minutes. Good.
Okay.
Okay.
Hey Gerd, how's it going? What, you sent a message there? What doesn't take? Oh yeah, the break, is it? Were you talking about the break? Was it? It continues. Doesn't take that long anymore. But yeah. So I put that video on. I think he's a pretty good speaker. Like, he kind of goes from one point to the next. But I'd say for you probably know most of that stuff anyway. I just clicked on that video randomly to see what it was about. Rajan's probably on a break.
The video from Emmanouil is not good to understand. It's a fast speaker.
Yeah, I didn't have too much problem understanding him. But yeah, you might want to go back and play it at top speed or something, Gerd, with subtitles.
I think I would understand more if he would speak Dutch.
Oh yeah. The other thing you could do is, I'm sure you know this. You hit show transcript. Where did it go? They moved it down here. And then then this gives you and you can even search for terms if you've watched the video before and you want to find the thing. And then what you can do is, if I go up here and toggle timestamps, and then you can select all of that and put it into a translator, and you can just read it in German. So that's one way to do it if there's no German subtitles. Another video I was looking at earlier today was this one. But, it's all about, what's your take on de Sitter and anti-de Sitter space? I suppose it's, your model is not really based on that. This guy's, I think this guy's also Dutch, I'm not sure.
And
yeah, he is.
To make that clear a little bit in this talk.
So there he's going on about entropy, dark matter, black hole.
Theory, indeed. Essentially, we call it something like the central charge, or the.
See this? So they have an anti-de Sitter space, and this is a toy model for a black hole. But they have, instead of it being positively curved, it's negative. So in this model, toy model, it seems like gravity works in the opposite direction somehow, which is a bit strange. I mean, if you were to just invert this hyperbolic field, then you'd presumably have a no longer a toy model, but a real model. But then you lose the boundary, technically, although you could just have a new boundary. But the interesting thing about this is you can stack all of these anti-de Sitter space disks one on top of the other to form like a cylinder. And then on the outside of that, you're supposed to have a complete Minkowski spacetime. Whereas, so anything that's moving on the outside of the cylinder, or no, sorry, anything moving on the inside of the space of the cylinder can be projected onto the outside.
Sorry, I tried to get the transcript. Now I found it. Thank you for the tip. But I did not watch your last sentences. Please.
Oh yeah, okay. I can repeat. That's no problem. Let me just think. Okay, so this is, so which part did you hear? Did you catch any of it? What was the last thing you heard? Okay, I'll just repeat then. So this is the anti-de Sitter space. It's like a toy model for a black hole. So this has negative curvature because it's hyperbolic, which would, so if the negative curvature I wonder, would that mean that this is like, instead of gravity being an attractive force, it's a repellent force in this toy model? Seems to me that.
Yeah, but a moment, it's a rotating black hole.
No, this one is. This looks static to me, I would say.
And that's where you the mouse cursor is. It's the outer Schwarzschild radius, and that inside is the inner Schwarzschild radius. Correct?
No, I'm not, actually. I don't think so. I think it's a bit different than that. This is probably the event horizon, I'm guessing.
No, it's very wichtig. Ach, Moment.
Well, yeah.
It's very important to make it unterscheiden. To distinguish between a rotating and a not rotating black hole, and
yeah.
Okay, das muss hier Aha. Oh, let's go. Please wait.
Yeah, no problem.
What is if there is no rotation, then the inner Schwarzschild radius is at 0.
Okay. Yeah.
Then the black ball inside must be must vanish.
Oh, right. Well, yeah. Okay, so that's a good point.
So I think that is a rotating black hole. Yes. Okay. You can go on. Yes.
Okay. Yeah. So, well, what I can do is just this might help in terms of explaining what I'm talking about. Oh, where'd it go? Sorry, I'm getting confused between which videos I'm looking at. Oh yeah, so I need to close that. You can still see the video there, I'm guessing. And then if I open this and then go. So this is also a hyperbolic tiling of a space. So we can see that.
Okay. It's like at the universe outside the Planck lengths are very small and inside very big. Okay.
But you see the size of this inner octagon, let's say, bounded by the yellow here. This is an area. And if you were to move in this direction towards this guy, it would look the same as this. It would just get bigger. So if you go all the way out to the edge, you'll find
an octagon resembles the octagon, the circles with the eye space.
Yeah, very true. Yeah, this is it. Well, we'll see. It'll be interesting to see how the connection there at some point in the future. Oh, hang on a sec. So what I'm talking about, well, what I was trying to get across was, he's saying that this is oh, sorry, hang on a sec. As we can see, this is constant negative curvature. So if we go back here, so does this. But he's saying it's a toy model of a black hole. So gravity is a negative force, but I'm assuming in relativity or general relativity, it's considered a positive curvature, is it? Like you would have, it's getting like, as we go deeper into the black hole thing, the metric gets kind of smaller and more squashed, just as it does here along the boundary. So therefore, if we wanted to recreate that, we'd have to invert our hyperbolic thing like this. So this is the black hole in the center here with 0 size, like you're talking about, so non-rotating. And then there's your metric, space metric, squashed. And then you go out, and then finally you get to the boundary, which is just, which would be infinite in a sense, which is all of normal space. So, maybe this would be the event horizon then, and then this would be towards the center. So complete inversion of
that's the event horizon seen from the particle horizon, and the other is the particle horizon seen from the event horizon.
You think that? So you have those two.
Yes.
Cool. So so I think he would be better off with the diagrams I just showed you there, but like you see, he's using a graphic from MC Escher here with the bats and the angels and the devils. So it's not like a really rigorous mathematical diagram or anything. It is a pretty impressive piece of art. So the thing is, you can stack these disks on top of each other. So if we go back here, you can stack a load of these disks on top of each other, and the edge then becomes a cylinder. And let's say this is your black hole here. So anything that's being attracted towards that will be moving up as well.
Attracted or repelled by the inner particle horizon.
Well, yeah, but I suppose this is a 0 point. So the black hole is here. So it's coming in, it gets attracted, and then because this is just one slice.
Yeah, the question is it attracted or repelled? But the direction is the same.
Oh, okay. That's a hard one to understand, I suppose. But
or both is correct, maybe.
Oh well, yeah, that would be a contradiction, right?
It's repelled and attracted.
Well, yeah, I suppose. Yeah, you're kind of looking at it from your model. Which is good, but I can only really comment from like maybe this. I'm looking at it from more of a standard physics model. What they'd be discussing is the black, like let's say the black hole is at the very center here, and then this is just so this is they've inverted the gravitational field. It should look like that. There's the black hole.
I think the most of the mass is there located there where it is very small and where it is very big. Then there is a little of mass.
Well, I suppose in a black hole, all of the mass is like concentrated at singularity. So it would have to be squashed right in the very center, like smaller than a pixel. And then so maybe the event horizon in that case would be around here somewhere. I mean, you'd have to figure out what the spaces are in this, because obviously it's just something I made. It's like a toy model kind of thing. So yeah, so if these are disks all stacked on top of one another to create like a cylinder, and then that's also time, I guess, going up the cylinder. So if you were to fall into the black hole, you're actually creating a world line that's going up the cylinder towards the center, and then that can be projected onto the surface of the cylinder. And then out here, they say that this is an actual proper Minkowski spacetime. So then you have like, you know, special relativity projected to in a one-to-one way onto general relativity. So it's interesting, but it's maybe a little bit confusing. So talking about binary, on the boundary, we have a finite temperature, and then the bulk, which is the whole thing, is what he's calling a black hole. So that's anti-de Sitter space. And then, whereas this one was de Sitter space. So with de Sitter space, you have like, let's say the Earth, we're at the center here, and then you go out. Well, I think technically a de Sitter universe is like, it only, when the universe is completely expanded and like has maximum entropy, then you have like a real proper de Sitter space with nothing going on in it. It's kind of like the heat death of the universe. But all of these stars and galaxies sort of get pushed out, and then they get projected.
Yeah, the outside is the view from yesterday, and at the beginning, the stars were very close to each other, and the density was very high, and much more than nowadays in the center. It's okay.
Yes.
Yeah. But
you can see that there.
But if you change your from the center to the outer, then you are in another center, and you see all. It's the same view, but from another standpoint.
Perspective. I mean, that's a bit kind of like what we're saying here. You know, out here the universe is hot and dense, and there's lots of stars packed together. That's actually quite a good picture of it. And then, except that's hyperbolic. But then if we were at the oh no, hang on a sec. I'm getting mixed up here. Yeah. Okay, I don't think it works really. Sorry, I'm getting confused between that and something else. But yeah, that's interesting. What they're saying here is that when you get to the boundary, because this universe has to have a boundary, all of the stars would be sort of glued to the boundary, and then there's this thing called a holographic principle, where they're saying that everything, all of the information on the inside of this space exists on the boundary and is holographically projected into it, which makes sense as well from my point of view, because a little bit like yours, Gerd, all of the boundary is a point on the hypersphere.
Yes, the more information, the less entropy.
Yeah, I guess, but I don't know. It
outside
seems like
is more information, and inside is more entropy.
Okay, yeah, that sounds reasonable. Yeah,
it's a shell. Yes, inside is more information.
Or well, yeah. So just as in your model, like this outer boundary can becomes like a single point at the north pole of the hypersphere, and then you have this in my model you have this that point is a projective point. But in their model, what they're saying is that it's a holographic description of the universe, which means that when the projective light is projected in to create like this galaxy and this galaxy and all of these other galaxies.
No, I don't use the holographic
principle.
Maybe in your model it may be correct, but I don't ask me about holographic universe.
Oh no, that's fine. Yeah, no, I'm just explaining what they're saying. So, you know, the way with a hologram, basically it's this interference pattern in a way that so when you shine the light through it, it creates the three-dimensional image. But you could also have it wouldn't just have to be the interference pattern for that moment of space. It could be for all moments, which would imply that the boundary contains all the information of the universe from its beginning to its end, frozen in a static state on the boundary. I don't know if they believe that. They probably don't, which suits me because that wouldn't work. Well, I don't think that would work in my model either. It wouldn't be. If they are suggesting that, I would have to go against them on that. But also, they don't have a hypersphere in their model, as far as I know, or at least they don't refer to it. And they don't talk about a single point like you're discussing in your model, and they don't talk about a projective. Well, they kind of talk about a projection because they're talking about a holographic principle, but because they don't have the single point like in your model, then they miss. That's where my model differs from them, and also in a number of other ways. So this wasn't too bad. I think this guy is also Herman Verlinde. He's Dutch as well, I think, and he is he works with Gerald van der Hooft. Am I saying his name right? The other Dutch guy, anyway, that we just watched. Gerard te Hooft. Sorry, just assumed there was a van der in there for some reason.
It's a presentation effect.
Yes, I've heard of this demonstration effect, right? There's a German word for that. What is it?
The Vorführeffekt.
How do you say?
Vorführeffekt.
Yeah. Vorführ.
It's coming from cinema. Film vorführen, der Filmvorführer.
Vorführer. What is it? Right. Okay, so it came from television or film.
Der Film im Kino wird vorgeführt.
Yeah, I like it. So let me think. Right, then they have this other. They go on a lot about chaos theory, which isn't really part of what I'm doing. And maybe it was a different video. Sorry. Thinking about a different video, but anyway, that was kind of it was something that they had done. That I'll stop sharing that, and I can. Looks like Gerd is back, or not Gerd. Sorry. How's it going, Rajan? You've returned. Oh, that's. Hey, you're on mute. See what I can get here. See if I can do a different presentation of sorts.
Yeah, now the computer is back. The computer is old, so it takes a while for it to prep up.
No problem.
But the computer has worked for me almost 10 years, so I had to change it sometimes.
Yeah.
The laptop,
oh yeah.
Some of them last longer. This one lasted longer, and still I like it. But at some point I will change it. because it doesn't have the processing power, to do it fast. And that's why I got in the morning, stopped because I had to reboot it, because I couldn't pull up the devices. It says you cannot pull up the audio and the video and all that. Without that, how do I do the conference? So I had to reboot it, and now, now it's working. So were you discussing the last 1 hour? And sorry, I got fed up because this person came for inspection, home inspection. So I spent a lot of time in that. So I got caught up in that. Were you discussing that the last 1 hour or something?
Yeah, what we did was we played a number of videos.
Oh.
I played one by Unzicker. The German guy. I think he knows Christian actually. Unzicker. And that was on topological defects and how they relate to the ether and I think torsion, sort of the general relativity, different aspects of that, but mainly to do with possibly to do with an incompressible ether. And so that one is probably the one that you'd be interested in, Rajan, as well, because I think you did a bit of work on topological defects before, did you?
Yeah.
Well, of course you have done. I mean, that was what you were. How do you say your expertise are in that field, right?
Yeah, I did like the material defects in materials, like dislocations and vacancies, dislocations.
Yeah, there's a lot about like dislocations, discrepancies, or they had another word.
It's called dislocation. It's called a line defect.
Yes.
That explains why the stress, the stress should be, the theoretical stress should be 10 times that. And there is a beautiful proof. We studied in the bachelor, in bachelor's degree, how the stress, you can explain by use of dislocations, how the stress is 10 times less than the theoretical strength. The dislocations, it's a wonderful theory, and you can use something called scanning transmission electron microscope. I used to use that. That's fundamental for material scientists, and you can see dislocations moving. Actually,
Yeah, this was the thing he was talking about. That
Cambridge, the person from Cambridge.
They can move, yeah, because there was some paper written by he was talking about some guy called Lamar or something, an Irish guy who did all this work back in the 100 years ago or something. But then he was also talking about dislocations moving like through a crystal or a lattice and at a certain speed. So is that when you apply a force to the crystal, though, is it? And then it's
So you have two types of dislocation, called screw dislocation and edge dislocation. Two types, and that's what and then they create places, the sites and things like that, where like for hydrogen, I study about hydrogen embrittlement. So hydrogen go in, and you can accumulate there. You can create cell, and then you can create cracks and things like that. So, I'm not saying very, very fast, but a lot of things involved. So I studied quite a lot on that. I got some original theory about that. Dislocation can form like loops, very similar to what the string theory is saying, very similar to string theory. I think you should be able to apply string theory to that, but called vacancy loops. And in the loop, you can create precipitation of crystals and things like that. And actually they use in electronics, in the electronic materials or integrated circuits, some of the ideas of when I was teaching that, I briefly taught a graduate level, bachelor's at graduate level integrated circuit material science. So in that one, we talk about how these can be used to create a quantum tunnel diode, things like that, I used to teach that. I used to teach mostly the material side of it. So I don't remember all the details, but when I go back, I can check that. The MOSFET, MOSFET, metal oxide semiconductor field effect transistor, which is used for memory devices. The MOSFET is my favorite, one of my favorite devices. And I explained that time. I could explain very thoroughly the material side, how they connect the material and the thing connect. I don't remember all of it, but I used to know inside out. I used to give tests on that exam, and they considered it to be one of the top tests in the world. I had given about signal to noise ratio. That's my last one, and that I worked on it. And that's my because some of the students were graduate students, so I gave this. How do you explain the signal to noise ratio? Because you have the amplification factor, and I think we still are working. I mean, I have published publication, it's there, but I think still we talk about that. That's why today I put error analysis. That's another thing very important. I think I have come up with that. I probably will publish. I had two publication in Canadian journal. You might have seen. I sent to you.
Yes.
In Gerd also, I think. In that way, I touch upon these things and the chapter I'm publishing. But the main thing is I come up with the error analysis. I don't know what Einstein didn't do that. In error, you have the diffusion. You have the solution of fixed diffusion equation. Fixed equation has both space and time, right? The fixed equation. So when you solve that, you got something called the solution is, it was always enumbering to be error function. Error function is function of x over square root of d times t. So space and time comes there. And surprisingly, I applied, I want to publish this eventually, and probably we can publish something together also, is that when you consider speed of light, you can adjust the equation. So you put the information, and you can plot it as c times square root of t or something like that. It comes out. So then you can see how the time varies. And I plot it. I get like a web type of thing. And it describes what's happening in the last few decades. I analyzed that, and it normally shows like a resetting effect. And you see that the timeline, when you look at the from the 60s, we always reset the global level. We reset to the 1960s. The pattern resets, and this explains why. And you'll be surprised that.
Sorry, wait a second. I got to interrupt you there. What do you mean by reset to the 1960s?
Yeah, that's a good point. See, I look at the events, how they are, and we should be progressing to 2020. But we switch back our history back to 60s. If we go to the television, television keeps track of all this, right? They always go back what happened to the 60s.
Do you mean like in terms of like? Do you mean what? In terms of revolution or something, or what?
Yeah. So you see the Israel-Hamas war, the Cold War, the Russia, Ukraine. If you look at all that, these things happened in the 60s. The NDB. The 90 minutes at NDB. You know about the Israel-Palestinian conflict, where Israel, they hijacked a plane, the PLO, and they went to the plane in 90 minutes. They rescued all the people. That was one of the top things in the 1960, 1970 level. It's called the NDB. You should watch a video called 90 Minutes at NDB. That place called NDB.
Okay. Yeah, I think I do remember hearing about that. Was that during the Olympics, did you say?
Yeah, something like that. It's connected with that. But it's a hijacking. That's where the hijacking started. And later on, you have a lot of those things happening, 9/11, things like that happening, right? But that's all PLO. The separate states, the Palestinian, the Gaza, formation of Gaza, the Israel occupation of that place, things like that. And still, that's a big problem. So it reminds, it's like a deja vu. It's like deja vu, coming back again to that. And the Cold War, again, Russia now.
There's also progression, but I know what you mean about things repeating. But there was a writer called, science fiction writer called Philip K. Dick, who had a theory that the universe, since Jesus came and then was like he died, that he came back to life. And then after that period ended, there was supposed to be another period where the Holy Spirit is poured out upon the world, so that people become, you know, just like what happened to Jesus when he was alive, he got the Holy Spirit, and then realized that who he was and all the rest. Well, there's more to, you know, he was like born again in a sense, and then so that's supposed to happen to everyone on the planet, or not everyone, but like a lot of people. And then they can like speak in different languages, or, you know, speak in languages that they don't know, or languages that have never been invented before, and still understand each other. So it's pretty interesting. But and that creature that is the Holy Spirit, or like that being, is how do you say? It is also called the Logos, which translates as loads of things, but it means the word. And it means, you know, it can mean technology, and just has a lot of different concepts involved. So, so the word of God, obviously, and then speaking in tongues and and different languages. So it's hence why it's called a word, I guess. So, oh yeah. So he said that when that happened, I guess there's another entity which is like the one that God is struggling against. You know, so there's two entities. You could call it like the demiurge, or maybe Satan. It depends on your perspective.
Like Satan or devil.
A bit like that, yeah. I mean, Satan might even be a different being that's further down or something.
Yeah.
I think. I mean, the demiurge might technically not actually be an issue anymore. I think that was the whole point of when Christ died on the cross. His purpose was So prior to Jesus coming on the scene, yeah, the Jews had this temple, yeah, where they would sacrifice animals to their god, and that was how they paid penance for their sins. So now they don't have the temple anymore, so they can't do sacrifices, so they can't make amends.
Paganism or pagans.
Well, no, they weren't pagan though, because they believed in one God. So pagans have multiple gods, but sacrificing animals. So they want to. That's what this war in Israel is about. Partly, you know, is to take back Jerusalem and get rid of what's the name of the mosque there? The Al-Aqsa Mosque, I think it is. Is where Muhammad supposedly went. He ascended to heaven on a donkey or something. I don't know what the fuck. So anyway, I won't go into that, but. Or maybe it was a horse, but he definitely did. He did fly around on a donkey as well, I think. But these are all different stories that came out long after Muhammad was dead. In the not the surahs, but what are the hadiths? So anyway, yeah. So just so you get back on track, yeah. So they want to destroy that mosque, rebuild the temple, so they can start doing the sacrifices again, so that they can pay for their sins, you know, because they've built up like 2,000 years of sin, and they don't have any way. If the world ends tomorrow, there's no way for them to, you know, recompense for that. But some of the Orthodox Jews and the original Jews, like, don't even agree with the foundation of the state of Israel. They think once they were kicked out of Israel, there was something about God said, or I don't know where they're getting this from. It must be in the Bible somewhere though, or
not in Torah, right?
Yeah, the Torah. But then they also have the Talmud. But so I'm pretty sure this is in the Torah though. Somewhere they're getting the information that they're not supposed to have a nation anymore, even though it's promised to them in the Torah. So that seems contradictory. And they're not supposed to. So they have a different view on it. Some of the Orthodox would be very militant about.
Yeah, it's kind of Exodus, right? Exodus, the promised land and all that.
Exodus, yeah. I think so
the
Yahweh.
Ten Commandments. The Ten
Yahweh
Commandments
said to Abraham, your descendants will be as numerous. Hang on, I can't even speak anymore. Your descendants will be as numerous as all the stars in the universe, or all the sand on the beaches, or something like that, and that. This land from, I think, the river Tiber to the Euphrates will be yours. So that's Greater Israel. So so they plan. So there's some idea that that portion of land is apportioned to them by God, so that's why they're there. They've come back, and they're like, you know, at the moment they're just working on their little patch, make sure get the Palestinians out, but then eventually, like, some of the greater plan for the greater Israel would be to have a full Israel. So that would include places like Syria, Iraq, and Jordan, obviously, Lebanon. So that maybe explains why these countries are, you know, have been having such a rough time for the last 50, 60 years, 70 years, you know, because they're on the chopping block for the greater Israel. So that's what's going on there, I think. But getting back to the point of the animal sacrifices. Oh yeah, so they can't do that anymore, and so the idea is, but Christians don't believe in that at all. Like, we would say, if you sacrifice an animal, you are, whatever god you're giving that to, is, you're not actually giving it to a god at all. It's a demon, because gods don't need blood or sacrifices, because
we also believe in that. It's similar thing. Yeah.
What in Hinduism?
Yeah.
Oh yeah, because you wouldn't be into killing animals.
No.
Yeah, because I mean, it makes sense. Like, God is all powerful, so why the heck does he need blood?
Even
like,
we don't eat. We like, I am mostly vegetarian, right?
Yeah.
So we don't eat any meat or anything like that. So.
Oh yeah, fair enough. Well, mostly, you say.
Mostly means I have tasted whenever a thing like friendship. So I should be transparent, right? I should be honest. So from that honesty point of view, I have sampled it. That's it. But that may be like 3 or 4 occasions. That's it. But rest of the time I'm vegetarian. I have not even eat. I eaten eggs at some point.
You eat what?
But eggs.
Oh, eggs.
Like omelette.
Oh yeah. I mean, there's nothing wrong with eggs, is there? They're not live.
But that I stopped. So I'm fully. See, I would say 98% of the time, 99% of the time, I'm vegetarian. You know, in my whole life.
Well, fair enough. Yeah. So I was a vegetarian for a good while as well, like 9 years or something. So yeah. And it was more of a it wasn't a religious thing. It was more well, I suppose in a way it always is, but it was, you know, for the same reasons. I suppose more along the lines of just the ethical, moral reasons. But then but I don't know, like, so in you know, in Christianity you're allowed to eat meat, but you're also allowed to eat meat that was sacrificed. You know, like if you go to let's say a Muslim, I think they have a thing where they sacrifice a goat or something. It's called Eid or something like that. Eid. And if you went to that and they gave you the food and you didn't know what the festival was or whatever, you're allowed to eat the food. But if they say, oh, that was sacrificed to our god Allah or whatever, then you wouldn't be able to eat it, because instantly you'd know that that was not going to Allah, it was going to a demon, or that Allah is a demon. Like, that would be the logic used there, kind of thing. So yeah, so then Jesus is in. Also, this is another. Well, the reason why we don't sacrifice is because Jesus is the last sacrifice to God. You know, so he puts himself on the cross and offers himself as like the sacrifice, the last human sacrifice as well, because that's also a thing in a lot of religions of sacrificing humans to God. It's in, for instance, it's in Judaism. You know, Isaac taking his son up to the mountain to kill him on the altar, and then the angel, just as he's about to do it, the angel goes, "Stop! Like, okay, we believe you were just about willing to kill your son, so that was the test or whatever." But then later on in the Bible, you know, there is several instances of well, there's at least one anyway that's documented of someone killing their daughter to sacrifice so that a war is won or something like that. So that's still a part of so basically animal land, even possibly it's never been written out, like, but certainly animal sacrifices are part of Judaism. So yeah, so Christianity just says like no more of that. That's done with now. So, but the idea is that there was this god, like a demiurge, that was actually a demon feasting on all this blood that was being offered to him. and that so basically, like when there's a sacrifice, this God kind of opens his mouth to get ready to swallow what it is, and so Jesus then like basically becomes a sacrifice, is eaten by that God. Because he can't die, he transforms that God. So then he's like moving backwards in time, then eradicating all trace of that God from history in a sense. But yeah, so that's the theory that I had anyway about. So when we say you know, the way God is outside of time, so then when he's discussing something that like will happen, it already has happened to them. So when Jesus is saying, oh yeah, I am Yahweh, he means that he joined with Yahweh at some point in the future, but that point in the future is his present then at the time. So he, when he says he is Yahweh, he means that he will be and was always Yahweh. So, but yeah, only
it makes sense with like we say about photons. Photons kind of fall into each other, right? Flow into each other. A photon can go into another photon. It can occupy the same space. The same way, the future, which means that the future, it can, you know, the future you can see in the past, kind of thing, like a reflection.
Yeah, sure, yeah. Well, yeah, so kind of got off the point there a bit maybe, but yeah, I think what we were ultimately saying was about the time in a loop thing. So yeah, there's another issue that Philip K. Dick came up with, that when that happened, so there's like this sort of dark, you know, the Earth is in a fallen state, and there's all of these dark entities from previous wars and like dead, basically the ghosts of dead aliens from like previous warring civilizations that live on the Earth. They're kind of like fallen angels or devils, if you like, at this stage, because they're, you know, they're all deformed, and they just kind of feed off all the misery on the Earth, you know, but they're not allowed off the Earth, or else they're keeping everyone kind of prisoner here. So it's kind of hard to say which is which. But anyway, so that's why, you know, you need salvation and freedom and all of that. But yeah, so when the Christians were, or you know, the early Christians were just about to like storm that place and destroy it, you know, it's kind of this mystical zone, I guess, called, right. So then when they're going to do that, whatever force or entity is in control of that, put time into a loop, so that time just repeats itself in what he calls a non-self similar loop. So every time it goes around, it looks different, but it is the exact same thing. Just so I forgot when that loop starts. It's like, you know, Jesus dies, he resurrects, then the Holy Spirit is poured out, then they're just about to win, then it goes back to before Jesus arrives, like not too far, or maybe some point in his life, and it starts again. And then, so we still live in that time of when Jesus was alive, but it's just been repeated for the last 2,000 years. Or no, about maybe, yeah, around that. Maybe, you know, like 1900 years or something like that. It's been just going on and on again. So that could, you know, you could think, oh, then we're like all being reincarnated, you know, again and again, because we're the same people just coming back again and again. But I'm not sure if that's the case, like, because it could be, you know, there's this concept that all the world is a stage and that we're just actors playing a part.
Oh, yeah.
So every time the new cycle comes along, like new souls and new people will come in, but they just step into the patterns that are already there. Apart, and they leave, then new ones come in. So it might not be reincarnation in the sense that we normally think of it, but it is like still essentially
repeating.
Like yeah. So it's pretty cool. I like that there's like,
my sister, when she was in high school, you know, they have these people who write what is called, you know, the other kids write in that like biography. So they write in their thing, and one of the persons had written this exactly what you're saying, and she used to show me. She's elder to me, And at that time, I was like the middle school, and she was graduating. So they have written, yeah, all the people are, it's a stage, world is a stage, and we are all actors and things like that. It's a famous quote.
Oh yeah, well it's an old concept. I think I remember David Bowie going. Is it actually
Shakespeare or pre-Shakespeare? I'm not sure.
But yeah, it could easily be. I think it's attributed to Shakespeare, but I'm pretty sure it's attributed to Shakespeare. But yeah, it could be pre-Shakespeare.
That's a wonderful.
So that's it. Anyway, I like that kind of concept. It's very similar to what you have in Hinduism and Buddhism, but it's
yeah, like you believe in Brahman, right? Recently, I have been analyzing about Brahman, and also we have two things. I think I will eventually write on that, but I want to write about error analysis. Error analysis I came across because I think earlier, even before Newton, people try to understand our diffusion of gases like airflow, things like that. And they came up with the idea of like Graham's diffusion, things like that, about gases. They study a lot about gases. And they eventually came with the thermodynamics of gases, right? The gas theory. So that was the important thing that time. And then, of course, Newton used later on about understanding gases in terms of the collision or on the momentum transfer, things like that. But in the diffusion, the solution, both time and space are there. You have the solution of error function, and the error function complementary. When I plot it, then I change the time scale using information in terms of converting that equation into information by using speed of light. And then so when you use the speed of light, then you have only time different. Then you get loops like cobwebs or web that coming in. And then I follow that. It says that the time now, and it goes back, the time goes back, and the pattern again repeats the 1960s, again go. It's like a feedback circuit mechanism. It keeps going.
Right, but how do you get the datum of 1960 or?
Yeah, I calculated approximately. I mean, I use observation.
What
the
I mean,
the datum is based on decades. See.
Yeah, sorry, go ahead.
Yeah, datum is based on, okay, you go logarithmically. You go from second to minute to hour. You plot on a different scale. So they are logarithmically, they all go in steps like that. And that hour, day, then the week, then you have the month, year, decades. So when you go to decades, what happens is that you follow that curve. What happens to the trajectory of the event, and you have to take into account. I use something called matrix protocol also. So you have to take into account what feeds in. So the fundamental theory, I think I put in the published paper earlier, but that my idea is that information, for example, goes from like a supernova or something into when the particle forms into that. And that information, that time is created within the particle. There won't be any time if the particle is not created. That I talked about last time, right? So each particle will have different clocks that ticks at different times. So the information goes in there and the time is created. The time goes from the particle outside. So that's how you have the flow. The flow of information into the particle or ourselves. Let's say we are the particle, goes inside, and then the time is created. The clock is created like Hodge PDP mechanism, whatever, and the time is created and the time flows outside. So this is the flow. But what happens between you and me? That's a different clock. That's called communication.
Rajan, you're not answering the question I asked.
Okay, go ahead.
Which was, how did you get the datum of 1960?
Yeah, based on this one, based on the speed of light, based on the light years, the datum is that what happens when you go, suppose you are light years, light is going fast. So what's the distance is traveling, right? So in the when you talk about year, I think that's called light year, the distance that's traveled in a year, right? So you have so many light years, right? light year, the light is information going to travel, or the light is going to travel that much distance. But what happens is when you have 30 or 40 decades, you have 10 light years, then you have 20 light year, 30. So what happens? That distance becomes astronomical. It's no longer associated with Earth. So we are talking about Earth. Earth will have, surprisingly, that information contained in it maybe many light years, but it cannot be more than certain light years, because that disconnects from the Earth. Nothing else has nothing to do with that. So that's the basis on which. So I say, okay, astrological thing comes, or astronomical things come, astrophysical thing comes from, and then you have the mesoscopic thing, the quantum level, the mesoscopic thing. So what is a mesoscopic level? You know, what's the distance of the mesoscopic level? That's the thing. So I came up with the idea that it can be as much as a few light years of distance. So
okay.
that's mesoscopic.
Yeah, I mean, that's I don't know if did you ever hear of a guy called Terence McKenna?
Kind of sounds a ring to my ears, but I'm not sure. Can you explain?
Yeah, I think I can show you this. So this is his book. You see that?
Yeah, Invisible Landscape.
Yeah, so this is a book he wrote. It's a bit scanned in, so it's a bit all over the place.
Scandinavian type of person?
Oh no, he's American.
Oh,
no, I mean it's scanned in. The book has been scanned in.
Oh, okay.
So basically, he has a theory of time that time would repeat over and over and over again in smaller and smaller. You know, like
loops.
Yeah, exactly. Yeah, getting faster and faster, and then the datum point would be in the year 2012. You remember all of that? Like the world would end.
The movie, right? 2012 movie.
Yeah, like the movie would have gotten its
Mayan thing. The Mayan.
Yeah, exactly. That was so initially he created this thing called the time wave. I'm just trying to find an example of it in this book. It's probably a bit further on. Probably getting to it now. So he used the ancient Chinese divination system called the I Ching, and he found he took a load of psychedelic mushrooms. There's the I Ching, and he met this entity, he said, in a forest, which told him that there was some sort of time code hidden in that structure. So off he went to discover it and you know, complete the mystery kind of thing that he had been given. So this book then is his attempt to do that. And then, so he finds this pattern in it, and then from that he creates the time wave. So this is the beginning of the time wave. You know, you have, these are something to do with the hexagrams, and then he puts it back on top of itself and finds that they join up perfectly at the beginning and the end. And then he takes a lot of Fourier transforms of that. And it's pretty impressive because he was a botanist and an entomologist and a kind of a scholar. So he taught himself all of this stuff, I guess, as well. And, you know, that's quite impressive. I think his brother was also helping him in terms of, he was a computer programmer. So, yeah, so he created the program for this. But I think Terence was the one who really developed it all himself, mathematically and all. But so this is all the preliminary work. You can see it, and then finally these are the so he basically the original thing that I showed you there, he just repeats it. It gets smaller and smaller. Then he takes the time wave Fourier transform of that, and he gets this. But this little bump down here is the same as this whole thing here. So it just repeats infinitely.
It's like a cycle.
Yeah, and it gets faster and faster, right? So that was it. And and then he initially said like, okay, this drop here was important. So he says, well, this is, or maybe it was this drop or this one, I'm not sure. But he basically pinned one of them to, you know, the detonation of the first nuclear bomb in 1947, or I don't know, I guess the Hiroshima nuclear bomb, so whenever that was. And then
1945.
Right, okay. You've seen Oppenheimer more recently than I haven't seen it yet. I know. I'm sure you know that anyway. But so then when you do that, you set that point, let's say at 1945, then this point here ends in 2012. But it was like I think it was October or something. And then someone said, oh, you know, the Mayan calendar ends in the year 2012. But the thing about the Mayan calendar, what?
December 21st or something.
That's it. Yeah, there's the winter solstice, of course. Yeah. So the what was the issue? So
it reminds me of your curve. Your curve.
Basically, someone says, "Oh, you know, you have this date. The Mayan calendar ends on this date, but it doesn't. I mean, the Mayan calendar is cyclical, you know, so it ends, but it starts again like every calendar." And they even had you know, they had what you call prophecies in their religion about like the return of a king, and it was set for like 2348 or something, I don't know, or 84, maybe even maybe it was 2600 or something. So so that's the point anyway, that so he just shifted it so it would coincide with the 2012 date, because I don't know, it sounded cooler, or you know. But either way, he was a bit of he's a funny guy, you know. He wasn't and I forgot what the end of the book is about. No, that must be it. Actually, I thought it had more equations in it, to be quite honest with you. I don't think it really does.
Probably converted everything algorithms to program it. You know.
Oh yeah, well you can still download the original program, and these are the outputs, you know. I'd say it's still around. I used to have a copy of it on my computer. TimeWave 0 is the name of the computer program. It's available in Mac or MS-DOS environment from Dolphin Software. But I think
it's a supercomputer, right? Is it like a part of a supercomputer simulation?
Oh no, absolutely not. No, this is well within the range of any normal computer. Even back in the day, they were able to. They did not need a supercomputer for this at all. So I think that's it. I just thought I'd show you that.
Do you use supercomputers in research?
No, I don't actually, because similar to what I just showed you there, my data is very just numeric, kind of almost univariate, you know. So it's not. I'm not dealing with big. You know, I'm dealing with satellite data, but it's not. It's sort of or how do you say, not metric, but like pretty much univariate, and it's not like image data from a satellite or anything. If I was dealing with images, that's like a lot more
number crunching.
Yeah, so a huge amount more data. So it's like, so then you'd need to use whatever clusters they have. They have these cluster computers, and then you have to send the information out and then get the response. So I'm kind of lucky that I don't have to do that. But in another way, I would like to start programming for those computers, because, you know, if you decide, oh well, I'll just make a very big program and look at like lots of info, it'd be good to get the result.
Like you said, you plan to come up with take a job in Hawaii, any place, you have to use supercomputers probably start.
Oh, cool! Yeah. Okay. Yeah, that's pretty good.
For weather, you know, for meteorology.
If I can get away with just using like a normal computer, I will. But at the same time, if it warrants, like if the work I'm doing is very heavy, then obviously I'm going to use the tool that works. But yeah, for the moment, I have no issues. You know, I can I seem to be able to do everything I need to do on just a normal laptop. So, but that could change, you know, in the future. I was thinking recently in the last week or two of certain ideas, applications for supercomputers, but really they mustn't be that important because I completely forgot about what they were. So I'll have to rethink it.
Yeah, on the side also. Yeah.
Huh?
On the side also, I'm thinking if you have like HAWAIIAN conference that you said, you know, probably hopefully in a few years, if not next year, probably. But I was thinking about on the IT side also, how we will display it. So I'm working on the other side. IT means more algorithm. So I'm working on physics on one side and the IT algorithm on the other side that can, you know, reduce the, my idea is to reduce the data, you know, and using matrix protocol. And I come up with a way that audio, video, and all those things, how you, and the texting, how you connect them. And I have come up with a very simple representation. Like I use something called a deck. I derive that, mathematically I derive these things. The deck, and the deck is like the input, and the input can be, you can do two things to the input. One is the, you can shift the input, but also paradigm shift the input. So you can move the inputs, and that's what's happening. You know, like I was in the school, I had some inputs there, and the input is connected throughput to the output. Throughput is like your computer or whatever that processes it, and then output is your screen. So you connect that. I measure, I go through the dynamics of that, and then I transferred all the information here for my thing. What I was thinking, it's like thinking level, and then I transfer it, and I have another place I transfer the input to that. So all these are continuous process, so that I don't miss anything, any information or anything, and I transfer it. And I found a nice way. The same thing we can do in Hawaii. If whatever we develop here, we can transfer it there, so we don't lose anything, any information, because you know there are a lot of information. You know, face it, information processing is one of the hardest things. Even with supercomputers, it's not enough, right? So much of data, and we cannot lose a lot of things because we are, for our physics, to develop the physics, there are a lot of things. Like I talk about Janot transforms, it's 20-page derivation, but eventually I have to show that also. So how many of that is important, you know? So what is a, you know, you prioritize and say, what's the most important thing? How much you can crunch that? How much time you need that? So when we talk about that video, you know, people don't have much time. So you can spend 1 or 2 days the most. So in that 1 or 2 days, can you explain everything, you know? So that is kind of, you know, how do you compress all these things into presentable thing that everybody can understand as well, you know? So that is the biggest challenge. And I think some of it I process it like filter, like I say like 4 filter thing, not only true, false, not false, and not true. So I can check out if it's false, remove it, you know, and I find that 40%, more than 40% is false. Then not true, another 20% not true. I can check out that. Then not false and true, I have to keep it. So that's about 40%. So 40%. So I do this loop, feedback that you do, you go through that, and you can remove a lot of the things. And I use something called 3210 logic. So which means that everything is taken care of, and I only worry about the last one, you know, close to the last one. I don't worry about, I don't have to, because all these are, you know, just to get to that point, right? So, which means we can reduce, instead of thousands of publications, we can reduce to like hundreds or even less. 100 publications is enough, because all of the things are considered junk. They are useless. They don't, you know, they have a problem there. That's the whole idea. So I want to compress within 100 publications. If I discuss 100 publications, that's enough for the whole science that happened from 16th century to 21st century. You know, that's the whole idea of my, you know, to compress everything so that we can finish within our lifetime all these things and unify everything. That's the ultimate goal. It's a very tall order, but I think I have some way I come across be able to do that. And I think one of the biggest thing is the diffusion. So that if I use that error signal analysis with feedback circuit mechanism, I can remove most of it, and all the quantum mechanics, all the relativistic theory, everything, standard model, everything will fall into that. So that becomes the bigger umbrella in which all this, standard model, supersymmetry, string theory, everything will come in that. That's the ultimate goal. Like Gerd was saying, the particle horizon, that's what I want to know. It's kind of very similar. Like particle horizon is within the black hole horizon. So that's a big picture we have to get. We have to ensure that it's correct. And then everything will fall into that. And then you have the web. You have like this, like the vacuum holds the time constant, I think, or the velocity speed of light constant. And then you are stretching. You are stretching of that thing, which will stretch the light. And that will explain about expansion and all that. So that's
looking at you on that because, but I think I spoke about that before. So, like on the hypersphere with the metric.
Yeah, the geometry you have to explain because you are a geometrician. You know better than any of us. So you have done a lot more on that. You have to interpret the geometry.
Yeah, I'll definitely show that stuff. I mean, it's very similar. There's a lot of similarities to my work now and what Gerd is doing. Gerd's obviously, the diagrams he showed us today. They're lots of angles and there's a lot of geometry in that. So I'd say I'd also put Gerd up there in terms of what he's doing geometrically. It's a different type of geometry to me. So like I think his work would probably benefit from what I know. I could, do a lot. And if he was to say, oh, I need this kind of thing visualized. If I had the time, I'm very busy. I can't even do my own work at the moment. So, the idea of doing that would be very ridiculous.
Your PhD thing? You are getting the last 2 weeks. You are busy. You are well on your way.
Oh yeah, super busy. Confirmation assessment. Then I had to write a paper really quickly for that.
So you are finalizing? You'll be defending your PhD?
Just they were like, so basically I had...
This year you will finish your PhD?
Oh, no. It's confirmation assessment, which is like kind of the beginning of it. It's like where they say, okay, we've seen your work for the last year. It's good enough. We'll let you continue kind of thing.
I thought your director or somebody was saying that you are almost done with your PhD or something.
Oh yeah, that's right. No, yeah, in terms of the whole layout of the PhD, that's all done.
But you take another few years to complete, 1 or 2 years.
Yeah, like the time scale is another 2 years I have left to finish. But so I was I was supposed to present a proposal there a couple of weeks back, and they were like, oh yeah, you're just meant to propose your idea, but you've done all the work, So they were like, technically you finished your PhD is what they were saying to me. But then with the requirements for that, they were looking for other things, which I didn't know about because I wasn't really told about them. So then I had to go back, do those. Then other stuff came. I had to teach. I had to prepare a class. I had to teach those classes. Then I have to teach. I have to demonstrate in different classes, and then I also have a lot of writing work and research work to do. And then I have my own kind of cosmology physics work, which I just haven't even been able to do. I haven't even been able to finish that slideshow to present here in the last 2 months or a month or more.
So you are like a TA, kind of like TA work, teaching assistant or something.
Oh yeah. They call it demonstrating. So
demonstrator.
Yeah, I do that. But then I also
graduate level, undergraduate level students.
Undergrads and they're all undergrads that I'm demonstrating with at the moment. But last week I was also teaching a class, and I had to, you know, make all the materials for that. And
you like a physics class?
It wasn't. No, it was
IT.
It was beginners Python, so it was nice and easy. But still, you know, I don't
more like programming. Okay.
Yeah, it was programming. Yes, so just teaching people how to program. It's a nice class. Not too difficult. I'd love to be teaching physics, but I mean, to be fair, I think I'd only
when we have at Berlin University, we'll be teaching gauge physics. We already.
Oh yeah,
I laid out the things. So.
Yeah, so I mean, I'm definitely interested in that because, like, I think, you know, I couldn't go in and teach undergrads physics, like the kind of stuff you did, and I just wouldn't have the.
I did high school physics. I was teaching. But undergrad, I was teaching material science a little bit. Yeah.
Right, yeah, but like anything like on that level with all of those, that complex maths, like people coming out of that, or, you know, the people that the research that we look at is very involved, and I wouldn't be teaching that. Like, all I would do is I would just have my work, and then I'd just teach that, you know, to people. Like the thing that I know, I would teach.
Each person will concentrate on their specialty, whatever they are good at.
Yeah. So that is how I'd go about it. So it wouldn't be a general class.
Like geometry, you can teach geometry of physics. Something like
that. So for me, it wouldn't be that I have to teach physicists necessarily. Like this would be open to like any, you know, it's meant to be open to anyone, effectively. But then the more we learn, the more we talk, you know, it starts to get outside people's comfort zones and what they know. And
I believe in interdisciplinary, you know.
Also, I mean, you know, a lot of the work you do would be above most people's heads, and Gerd's work and Christian's. So that's, you know, if you were like, if Gerd was going to teach his thing to a group of people, he would have to start at the beginning explaining what he means by subspace, what he means by.
That's why I think I get a better idea today after a discussion. Before, you know, because I had general idea when he discussed, but things are like, you also agree that it was all over the place. I couldn't understand what exactly he was getting at. Today, you are questioning.
Like the metric universe, it's just like he starts maybe midway through the book. Because he's like, you're in it now, and then it goes for like, I don't know, 1,000 equations. You know, so instead
you are Puri help, because you are a way of really, you should be a moderator, you know, in the sense that you should control the thing. So you are good. And good skill in that. You have good skill. I have to congratulate you on that. But then I could chip in.
Well, this is it. I'm sitting there listening to you, Gerd, talk, and I'm assuming that you and Christian and whoever else knows what he's talking about. So I'm like, maybe I shouldn't interrupt you and ask what is this? Like, define this word. But then it's fine to do that later on.
I can understand general terms, not specific.
It's the same with everything, you know. If we're going to present our work to people, you need to start at the beginning, start simply, and explain. You know, people who
distill it down.
Build on that, and then get to the point that we're trying to
ideally, you know, I like to start ideally. I don't know whether it's ever possible. How do you get 0? How do you get, like Christian doesn't feel, how do you get 1 + 1 = 2? Things like that. So you start from elementary school level math. I teach now also and then graduate step by step, go up and then go to that level, you know. But each time you have to reset. That's why I believe it. You have to reset and come back. Like you come back and then relate to your fundamental math again. That's your basic principle. And how do you relate that? Like metric field. Is there a metric field versus a metric space? Metric space is very different thing. You have the what you call topological field. I mean, that's a whole math. You know, I went to a library, the whole section, like you know, topological field. What's that person's name? Famous guy. He has done this one. And the whole section of the... Huh?
Oh, no, sorry. I wouldn't know. Yeah, go on.
Yeah, the whole section is devoted to that topological space. And he defines, he has theorems, proof, millions of things going on,
Right.
So, I said, what is a metric space? What is a topological space? What is all these things? And now Gerd is talking, he's not talking exactly that. He's talking about metric universe, which is...
Yeah, slightly different thing, isn't it?
Yeah, it's a subspace. What is a subspace? That's what I want to clarify. Is the subspace, so if we can clarify that, that's the question I have. It's a subspace same as the vacuum. Is the metric field same as our subluminal thing? I think then we are combining Emmanouil, myself, and your work with Gerd's work, and also Christian I space. Where does it stand? Again, Christian goes off a tangent on his thing, right? But again, bringing back, I think there's a connection. Bringing back to the thing, what is the I space? How does I space fit into the thing? Is the I space talk about the black hole? Like Gerd is talking about the whole universe is inside a black hole. Does the I space support that?
Oh, yeah. Well, actually, me and Gerd were, I think, while you were on your break or while you were going to meet someone, we did a bit of work on de Sitter spaces, anti-de Sitter spaces. And so I was showing him that work that other people
let me clarify about, and I don't know whether I'm correct. Sitter spaces, you are inside and looking outside. Anti-de Sitter spaces, you are outside looking inside. Is that right?
No, not really.
Sphere,
well,
like
yeah,
a sphere, like a sphere.
Kind of, yeah. That is kind of
sphere.
true.
You are inside a sphere, inside a box, and looking outside. That's a Sitter space. Like you are inside a sphere or something, and you are like within Earth and looking outside. That's a Sitter space. And then you are looking outside the Earth and looking into the Earth. That anti-de Sitter, something like that.
Not quite. But you can watch the video and it'll explain it. If you watch back on the bit that me and Gerd did while you were gone, I explain it all there in a pretty straightforward way. But some of the graphics that I use to explain it contain these cells, that are arranged all over the place in anti-de Sitter space. And Gerd quickly pointed out, he was like, oh, that looks like Christian's I space kind of theory, which is relates a lot to my current work. And so basically I should be able to, in some sense, bring in Christian's work into mine. Gerd's work obviously might be a bit like, I think Gerd and myself are kind of talking about the same thing. We were both talking about a very geometric thing, but I think his one is in a space-time. So it's like, it's a different, like mine is just dealing with space. Although I do have space-time elements in it, but it's different. So, and then, if you can figure out then the connection with Gerd's work in subspace, which he thinks is a plenum, by the way, like an ether, but also seems to be related to
like
zero.
John's cleanup, probably.
Kind of, but also a like 0 point energy field. So then, I think he did discuss the superluminal aspect with you today. So I don't really, I'm not sure if I see a connection there. But if you look at my work, there is, I have, well, he says that there's no, well, he doesn't have superluminal, but he has instantaneous. And that's true of my work as well. I've got the flat space, tangent space, the hypersphere, and then, so anything, the light moving inside the hypersphere or on the tangent space moves at the speed of light. But the other light rays that are projected from the projective point at the North Pole of the hypersphere, that all of that information is instantaneous. So you have our universe, which is a subspace, which has luminal and obviously subluminal being matter. but then we have light, which is luminous speed, and then the superluminal realm, which kind of, in a sense, cuts through those three, the other two realms of the hypersphere and the hyperplane. That is your superluminal realm. So, but I don't think that is maybe that satisfactory for you guys, because it's, you know, it's done. Like, that is mapped out. I don't know how much you can do with that, really.
Yeah, one of things.
If I'm not mistaken, just you like to take things, ideas from places, you know, what you come across, and then sort of adapt them, make them your own. You're not necessarily interested in working within someone else's.
No, I want to process. I'm interested in information processing, in the sense that all that information, but you have to compress. I am interested in compressing the information.
Oh, yeah, but that's
so
different
that,
work. I mean, you haven't really, like, fair enough. You spoke about that tonight, but yeah, I mean, there's you know, something to what you're saying there, but that's also a huge area. You know, if you're talking about actual physical stuff, then you're talking about building chips and getting over bottlenecks, and then you're talking about transforming visual imagery into sound and all of that. Well, we can do that already, you know, because we convert it all into electrical signals anyway. So that's no problem. Like, we can listen to visuals and we can look at sound using a computer. So all of that's already done. Now, if you're discussing like compression, file compression, data compression, well, there's a huge amount of work done on that as well, and you know, you can look into that. It's very interesting. But then if you want to apply that to all of science, like all of scientific knowledge, and somehow compress it, and then maybe reproject that somewhere, somehow.
No, yeah.
That's great. That is an interesting concept, but that seems to me more like, well, it reminds me of like what James Joyce did. Did you ever read Finnegan's Wake? Do you know Finnegan's Wake?
I don't remember. I may have.
Okay, so it's a book he wrote, and basically it starts off river run past Eve and Adam. So the first line doesn't have a capital letter, yeah? It's the first line starts with a lowercase letter, and then it goes river run. So it starts with Eve and Adam. So it starts at the beginning of human history, and then the whole book is just all of human history, but it's all compressed, like, so it's basically illegible. You know, the information is so densely packed. Like, one word can be like 5 words compressed together with different languages. So you have to know like 5 different languages to understand the word properly and what it's saying. And
like
then you get
Latin, Sanskrit, they are all very similar. You know, that's
that's what he's doing. He's finding the similarities in words, and then they're mostly they're just jokes. You know, he'll put like, so they're all plays on words and plays on each other. And then
I use that kind of like that in matrix protocol. I use
thunder words as well. You know, which are words with like 100 letters in them. So, but and they're just meant to compression of data that stand for something specific within some sort of religious concept. And then the end of the book just loops back over to the start of the book. So the book has no ending. So it doesn't have a full stop. And that's the reason why there's no capital letter at the beginning. So yeah, if you could do something like that with science, like compress all of science, but then have a way of decoding it. So, but
yeah,
you know, like, I think really at that point, you'd be better off going into like what Joyce did, and just write like, you know, scientific literature that is like Joycean, like almost incomprehensible. Be funny. I don't know if it'd be very useful to anyone.
Yeah. So another thing I found is a common, very simple principle of how I explain that matrix protocol. So I came up with a simple graph.
Oh yeah, I think you explained that to me before, Rajan.
Yeah, it's like bit and byte. You know, like byte is 8 bits, right?
Yeah.
Very similar, but 1 bit is like a word. one word is like a bit. So you have octet is like the byte. Octet is like a byte for the word. So which means that everything is compressed into that. And then each letter, each word, finally, when I do metrics, it has only 8 character, 8 alphabets possible. So it limits that. Again, bit and byte, microbit, microbyte, you can say. So it uses that principle, and that's what I use. So then it uses how that communication protocol you can create, and everything is fit into that, everything is transformed into that, or transfer all the information that I get into that, so you can analyze them in terms of, it's something very similar to bits and bytes, like computer does. So very similar idea.
I think we kind of already have that, don't we?
Yeah. So I think I have put a simple design also in one of my the recent Canadian, the CJ Pass publication. At the end, I have put how do you combine chat GPT, GPT-4, internet, television. So I have come up with like a circuitry, like super circuitry, and some kind of algorithmic way to combine them. So we can automate many of these processes. I mean, that's an idea, but an IT person like you know how. That's an idea, But from there, you can probably develop more logistical way, more practical way of coming out with an app or a program that can do the job, Because I think ChatGPT is fairly good, except it has a lot of problems. So we have to keep monitoring the references, comes up with some fictional references. If we put a hot PDP mechanism, it does nicely, it explains very nicely. And then it come up with the references that we never publish. It's like fictional references. These references show that, So we have to watch out for these kinds of things, But other than that, it's useful, very useful. Actually, it's quite useful. You have to be very watchful of those little. You have to edit that. Be careful about those things. Take it out. I did that in one of the detailed survey for my meeting chapter. So it's quite useful in that sense, And so you put in. So that's the idea. Idea is that I come up with a communication string. I call it communication string. That comes from matrix protocol. So there's matrix 1 and matrix 2. Matrix 1 is the beginning, the starting thing. Like if you are looking at a video, like our video, matrix 1 is like a starting point, but that is defined by certain algorithms, certain rules. And the matrix 2 is where it ends. So this comes from fundamental communication logistics, logistical analysis, like language to logic and logic to language, that kind of translations. So I put them together, like the languages, like Greek, all these things come. It's kind of like that, compressing the thing. So use that. Then it comes with a communication string. That communication string will explain, and you can put that communication string into the chat GPT, and then it will spill out. Like you want to make a movie. For example, I came up with something called A Thinker Who Became an Actor. Okay. So suppose you put in I would think eventually you put into a chat GPT, the chat GPT will come up with the whole script for that one. And you have to put some things in between, some other things, but it'll keep prompting. Okay, you have to put some more things, some more details, and then come up with the whole script. And that script can be used to make a movie, right? So that's the eventual idea. So our thing also, we have all these YouTube videos, and we put a communication string for that into ChatGPT. Then we will ask for that. So he'll process the whole YouTube videos and then make it into a movie. And that movie, we can put it in the HAWAIIAN conference or somewhere where final conference. So people look at it, they get an idea of what we did or what that physics is about, and eventually compress everything. Like then have Sapir-Whorst field. Some few people like Lisa Randall, what is the Stanford person, a famous guy who was actually rewarded recently. What is his name?
Susskind.
Stanford. Susskind, yeah, Susskind, Leonard Susskind. So, like, they will be some of the honorary speakers, and then we have this compressed thing that explains from physics from 16th century to 21st century, like a movie. So we put that movie, and it contains everything. And my error analysis will be there, diffusion, how it started with the diffusion gases, then how Galileo came up with the gravity, then Newton, then you have Maxwell and other people coming into picture, then you have Einstein and Bohr and Schrodinger, all these people, and then new people with Penrose. And,
it sounds like an encyclopedia of
yeah.
But don't we all, like, we have Wikipedia there?
Yeah,
you know?
But that is like a movie, like Oppenheimer movie. You can have the movie that will show the history of physics, kind of.
Oh, okay, yeah.
Like in a gumption, So if people look at that movie, few hours, it may last a few hours. You may not finish in one sitting of movie, but let's say movie is like 2 to 3 hours each one. You may need like a few episodes, like Star Wars, but not too many. Maybe maximum 10 episodes, and that explains everything of the history of physics in a gumption. So people may have some time like that. Probably people can watch 3 or 4 movies. I don't think they will have much more time than that. In general, people, like, even I see that it's very hard for me to sit down watch movies now, so I don't have that time. But like Oppenheimer, I saw a few movies like that, very important movies. Then the top people who are so busy, even including you are becoming a very busy person. You are already are. And like many of us, like Emmanouil is not able to come. Wenzhong and John now is, he's working in the research gate, but he's putting idea. He said he will read my CJ Pass papers. I don't know. He will get back to me. But he said he will read that when I sent him. Then Emmanouil has not come for a long time. Gerd Christian has not come for a long time. So the idea is that if you have a movie like that, all of us can probably sit together and or watch that and be able to get an idea. And the idea is that then becomes a way to blog further based on that. Everything is developed from that, and we can see how the unification. We can find a unified physics based on that. That's the eventual goal, that's the super goal, you can say, of the next decade. It may take 1 decade, like up to 2030 or something like that, or even more. I hope, by 2035, I'll be too old. I'll be off. But up to 2035, if I am alive by then, at that time, I'd like to be active till about that time. I'll be in the 70s, I think, by that time. But hopefully that can be done. And that's the whole idea. That's the idea of Hawaiian Conference, to have people start that process, and then, well, by the time we have World University, it will all be in streamlined, streamlined, that we can make like movies, and then watch the movies, and then start blogging, start discussing the auditorium, and then debating and all that. Because now we are on the same page. I don't think people are on the same page, because I don't understand. I mean, we have cross section. We have to find out, like, what I space. Somebody asked me what I space is. I can only say refer to Christian for that. If I be very fast, I can explain some of it. The same way Gerd's metric universe. What is it? I can explain maybe right, but refer to Gerd again. And then the geometry that helps we are thinking you are done. Emmanouil's work, same thing, So, but we have to have little more specifics that we need. So we have to inquire more each one. They write a précis, précis writing. I believe in précis writing. So, like Christian writes like less than 10 pages, 5 to 10 pages, the maximum. The whole of iSpace, which will explain everything, which connects to classical mechanics, quantum mechanics, and relativistic mechanics, all that. Also simple physics, simplifying physics. I believe in that. So start from very simple Newtonian equation of state, equation of motion, very simple thing of speed, velocity, and all that. Connect with that, and then geometry in terms of Euclidean, two-dimensional geometry like circle, three-dimensional geometry like sphere, then four-dimensional like toroids, all that. They explain all that, Mobius strip, whatever, Mobius transforms, things like that. Explain all that based on that, and you have to transform to that platform. From that platform you talk about and your thing, then people can understand. That's the same page. So the platform will be the same page. That even high school, if I put a high school student, should be able to reasonably good high school student probably, and that high school student can explain to the other his people, but his co-classmates that, but that person may be average or above average, so he can sit there and they can understand that. That's how it should be. So if they sit in that class, they should be able to understand what Gerd is talking about, what we are talking about, and all that. So that's that translation each person has to do. Each of us have to do for that people to really appreciate and also communicate with us what we are doing. Otherwise, it will all be a lost art. We don't want that. I think we have done a lot of good work, but it needs translation. Translation to simple, like Occam's razor is one of the ways, or simplified physics we have to do. So that's what that should be our goal towards our Hawaiian conference. And by that time,
yeah, that's true. Yeah, I'd agree with that. But I guess one issue would be the well, just like you're saying, how busy everyone is, and then whether or not. So yeah, like once I get a bit of time, I'm going to put together a slideshow, I guess, and then present that. And it'd be interesting to know if at the end of it, like you say, did it hit the mark? Does everyone now know what I'm talking about? Because I think with Gerd's work, like first of all, it's not been laid out in a way that we can like quickly understand what he's saying. And secondly, it's also very technical and probably quite advanced. I mean, we're kind of getting the idea now what he's talking about. And also there's a little bit of a language barrier which slows things down, but not so bad. But I think we're getting the picture now. But I think the picture that we're getting is that what he's talking about is pretty complicated. So he's probably the only person who's going to understand fully what he means. But at least if we got the idea, like, explain it to us like we're 5 years old or something. So that's good. And I think we kind of follow what Christian's doing, although I'm not even sure Christian knows what he's doing, because the way normally you'd have you'd have some sort of geometric structure that explains everything you're doing, and then you move out to the mathematics to sort of describe your explanation, and then there's a third one, experimentation to prove what you've done, kind of thing. I think what is it? Christian has the maths, but his explanation for what he's doing in the maths doesn't make sense. At the moment.
So
some level, just geometrically, it doesn't make a whole lot of sense. But maybe there's so that's a bit confusing.
So in school, what we do is something called lesson plans. Probably you know that. So you break it down.
The other day, but I had to do my own lesson plan. So it was
break
fine.
It down. The idea is that break it down. So what happens is that two things. One of them is you have to, probably you and I, or if you can think of it, come up with a slew of questions, like maybe like 100 questions, one lead to the other to each person. So they have to answer that specific question. Very simple. You can start with what's the concept or something like that. We have to rethink about that. But then it builds up, and then finally it builds up to the math. So like you said that what I wrote about their discussion, Gerd Emmanouil discussion, you like the idea that the quantum mechanics may be describing the spin, rotation, and the revolution, whereas classical mechanics may be describing only rotation and the revolution. And you said that you like that explanation, but then we can develop the math to show that. And one of the hints, okay, this may be like a take-home exam in the physics when teaching physics, will be use my transform and prove that. So one of the ways you can do that is, if there's no spin, like a spin angle, you can put that as 0, right? So in the transform, then you compare the rest of them transforms. It is very hard because it involves Fourier, Legendre, Laplacian, and all that. So then the transform, you compare the two transforms and the angle, everything has to be same. Then you can prove that's a factor of 2 comes in the picture. In fact, you may find, and my intuition says that it may not be exactly 2, maybe 1.99 something, or 2 point something. The error is within that 2 plus or minus within certain error. That's what we'll come up with. So it may not be exactly 2, but we can approximate to 2. That's maybe how it may, the factor of 2 may become. That's my intuition is saying that from what I can, what I could see as a solution, because the transform is highly complex, actually, I showed you before, right? So, but very putting there, maybe the factor of 2 will pop out from there, come out from there. That to be a complete mathematical proof. That's a perfect mathematical proof of 2, of the factor of 2. Because what happens is that what quantum mechanics, the classical mechanics that considers the nucleus as a fixed point, and the electron as a particle, which is a fixed point, and the particle is moving around, right, rotating around. That's what is the classical mechanics. Whereas quantum mechanics says the neutron itself, the nucleus itself, the proton or the neutron itself spins around this axis like Earth, and the electrons are spinning around this axis. So it's like the Earth, Moon, and the Sun, right? Earth is spinning around, the Moon is rotating around that Earth. Then the whole thing is revolving around the Sun. So it's like your orbit, like your astrophysical model of Earth, Moon, and the Sun, very similar. So then it becomes highly complex. Maybe they were thinking about that it's too complex to handle that, so they simplified. Okay, you can consider as a fixed point. But I think now it's time you have to consider those things. So I think my transform has taken into account like hot PDP mechanism. Has taken into account that. That's why I had to complete that 20-page derivation. I think it can be used, and hopefully, and that's a big project. I don't even know how to do that. It's very similar to what this person did for Einstein thing. What was famous guy who proved that the black hole? I'm missing that person's name. But he was the first person to develop the black hole. He got all
Schwarzschild.
Short-side. Yeah, short-side. So he looked at Einstein equation, which is highly complex, like general theory. But he found
a way within like 2 months or 3 months of the thing being published.
Yeah, he did a fantastic job of converting that Einstein thing, which is totally mathematical, which cannot be decoded. He not only decoded, and he interpreted in terms of black hole theory. So something like that you need for. And then if you prove that, it's like a formula. You can say this is a formula and use that formula, and then it contains everything. So then you prove that if you don't have a spin, then you get the factor of 2, and that will be a complete proof. That will be a very rigorous proof, I think, of why we get 2, and that's a purely mathematical proof, which I believe will be the holy grail of the whole thing. Because, like I said, like Newton looked at it, bending of light, and then there's a factor of 2 there. Same way Einstein came with mc square, the speed of kinetic speed, and this kinetic, which is classical equation, half mv square to mc square. Of course, the m is different, it's relatively adjusted, but the idea is that the factor of 2 comes there, and now and Emmanouil is pointing out about the momentum thing, the classical momentum versus the, the quantum mechanical thing. So I think this factor comes into picture, and you being analyzed, you are gone very deep into the geometry, you will probably be able to pull out, from
yeah, that's interesting. What you're talking about the factor of 2, yeah. And Emmanouil had his diagrams of like straight line, like triangles with the hypotenuse, and then shading in the area underneath.
Yeah.
And then you were talking about how the difference between the classical and then the quantum could be the fact that the classical has a radius essentially with a central point that isn't a fixed central point, and then the outside is moving at a speed, whereas in the quantum mechanical sense, in the philosophical sense, you're talking about a point particle which has no center and no edge in a sense. It's just a point. So, like, I'm thinking about that would not in a geometric sense, but just in maybe an algebraic sense, I guess, but not even using algebra. But so I'm assuming that if we were to take the function from the fixed central point out to the radius in the classical version, that's just going to be a linear function of distance, like whatever the distance function is with the speed rotation. So I'm guessing that's going to be a linear function, which is basically what Emmanouil had anyway. But Emmanouil seems to be doing it in a slightly different way. Like those kind of right-angled triangles can be used to map out the area of a rotation, like in Kepler's work. So I'm not entirely sure what he was doing, but it could also be used to map out like the distance that a particle has traveled since the beginning of the universe. But then that distance would be just the length of the line. So I have no idea why he was including the area underneath, and then the area on top as well, which you never do. So
I have to look at it again.
Do you think I might have misunderstood what he's saying?
No, I have to look at it again and then reanalyze that, because I just scanned it.
Well, but yeah, fair enough. Yeah, that's okay. But so just going back to your point, then I think, so with the central point, if that's a linear function, then it will be a line. And then you can take the area under that, though, because it's, well, I've forgotten why, but I believe that you could take the area under that and it would make sense. Or at least, well, even that line would make sense. And then because you're saying there is, in the case where there is no radius in a sense, maybe then you could take the other half as an explanation.
But probability is an area, right? If you do probability distribution, you have to consider the whole area, because
you see, you guys, if you and Emmanouil, like, what is he? Is he a professor or is he a?
Now it's a postdoctoral.
He's a postdoc, post-grad, right? Postdoc, yeah.
Postdoctoral.
Right, that makes sense. But you know what I mean. So yourself and Emmanouil on that front would have probably be able to look at that and go, oh yeah, okay. Like, yeah, so probability area function. I know you'd have to send me on something about that so I could look into it.
The probability usually use the area and area under the curve or something like that.
Right. Yeah, I think you're right. Yeah. Okay, maybe
so you have to look into that. I think that's how it comes about, the area.
Well, yeah, it could be something like that. Yeah. Isn't there also a lot about expectation values and all?
Yeah.
And all of that stuff, I have to say, drives me absolutely mad. I don't get it.
I also had a lot of difficulty with probability, but then I did it my own way and compare it. And sometimes, I'm slightly below it. Sometimes I'm above it. So I thought that, okay, I understand from my point of view, and I have taught a little bit probability and statistics in schools, So when I started doing that, I started understanding, because I didn't understand the whole concept, probability, how the probability comes in. It seems to be too contorted, or convoluted, so to say. Like
well, I mean, even some of the other stuff I'm looking at, like the Clifford algebras and stuff.
Yeah, I was thinking about the Clifford rotation, Grassmann rotation. That's another.
No. Clifford algebras are different to Clifford rotations.
Oh, okay. And I'm saying that.
Yeah. Clifford algebra is like a dual rotation. That's all it is. And a
what?
Sorry, a Clifford. What did you say again? Clifford rotation is a dual rotation.
Dual?
Dual. D-U-A-L.
Oh, dual rotation. Oh,
yeah, it rotates in two axes at the same time.
Ah, okay. How about Grassmann? Grassmann is 90 degree, right angle to that, right? Or something.
I don't know. I'd have to look that up. That's an interesting question. But then Clifford algebras are they're just used to determine whether a particle has what its chirality is. So and all it does to do that is simple matrix multiplication along with one of those gamma matrices, you know, the ones, the Dirac, is it? Or
Gelman?
I don't think it was Gelman or Gelman. But anyway, so the gamma matrix, you know, I think it's gamma 5 or something.
Oh, the gamma function. Okay.
Yeah, so that's, and then, but that's all it does. And then it just gives you the correct answer for, you know, for like what?
Mirror symmetry, right? So it's mirroring. Like X and Y becomes Y and X type of thing. You know,
no, it's just a simple matrix multiplication. So your column vector with the, oh yeah, I suppose, yeah, X and Y, yeah, you're right, sorry. I had to, okay. I was just,
because you have mirror rotation, you have a mirror and you are reflecting in the other side, X becomes a Y and Y becomes X or something like that.
Well, yeah, I mean, I don't know if we're exactly talking about the same thing, but I was just about to explain it, and basically that sounds right. Like well, actually, no, I'll just clarify what I'm saying. So you have a column vector, let's say, with two entries, X and Y, and one of them becomes 0 and the other one becomes 1, or sorry, becomes the wave function for your thing, like your psi field waveform, and then then that flips. So the other one becomes 0 and the other one becomes psi or sub or, you know, for right-handed, and then the other one is psi sub L for left-handed, and so on and so forth. So but that's really it. But the thing is, it happens to be like an equation, so you can fit it into other equations, and then when you manipulate your original equation, you are manipulating and changing the original equation, if I said that right. So it makes sense what they're doing in a way, but it's also, I suppose it's only useful if you're like that advanced anyway, that you're going to be working with that and maybe relativity and differential equations with the field theories and all of that. And then, okay. But I mean, even so, all of that stuff is just represented by one single symbol. So when you do differentiate it, I mean, are you unpacking that symbol to differentiate, or do you just skip over that and just do it? And yeah, I've noticed that a bit about relativity anyway, that working with it just seems to skip over a lot of stuff, and it's like, oh well, we have D here, and then this becomes this, and it's like, well, that's really easy, but the actual field is not easy at all. So I don't know. I'm stuck between like knowing this.
I watched some of the
videos. Equations going, I just don't even understand that. But then I think there's a similar thing that I don't. I think I looked at some of your previous work on the S4, sort of this matrix that you had with matrices inside it, and then within those you had gradient fields, I think, which are also tensor functions or something. So, and then the notation you used for that, I forgot what it was, but let's say it was like G and so
epsilon G, epsilon mu G,
mu, that kind of thing, and then you have it up top with the covariant vector and the blah blah blah. But then and you're saying that's describing the gradient or the curl field in this tensor mathematics or whatever. Then so I'm just curious, like, you know, how that really works, like in a practical sense. Like if you were to convert, I don't know, a gradient field into a vector field using tensor equations, like presumably that would be a fairly complicated process. Or certainly no different to the one where I was asking you to take the metric and transform it in a certain way. So I think it'd be interesting to know how to do those kind of things, though. But
two things you have to do. I mean, that may be a starting point. Two things are unitarization and normalization. So unitarization is like you come up with a unit vector or unit tensor, and you convert everything else to scalar. And then normalizing is where, you know,
I know what normalizing is.
Yeah,
everything's between 0 and 1.
Yeah,
yeah.
So you have to do that, and that may help. That may not be sufficient, but that's necessary. That may be a necessary condition.
I'm not entirely sure I understand unitary conversions.
Unitary means, suppose I have epsilon g, and that's talking about the whole thing, right? You convert it to eigenvector or unit vector like n or something, which will describe the unitary. And the other one is cardinality. Cardinality is where just the measurement of the length. For example, it converts to a rotation versus a rotation, like you are converting from Euclidean normal geometry to spherical geometry, rotational geometry. What do? Like x, y, and z, right? So you have x, y, and z, and you say x is a unit vector n times, which describes about the rotation, times some scalar function, L or something.
Whatever. But that's
L,
really easy.
That's a radius.
It's pretty easy. That can be very easy to do, but
if
you want to do that with you want to do that.
That's a starting point.
Usually you have to convert your Cartesian coordinates, let's say, into spherical coordinates to make it easier, your life easier. But so that's a different issue, maybe, I think. But I'd say really what you're talking about there is a lot of it's interesting what you're saying, but at the same time, it's not really that helpful. I suppose it's kind of a bit going back to like what we said about Gerd. You need to lay the foundation for things and then move to the next step.
So we have to come up with a set of questions.
To know, because you don't know what I don't know, so you don't know what to tell me. So
the algorithm, like that algorithm, you set up. I had once, I was working with somebody else in the IT guy. I told him, can't we convert it? And then, I want to do this research. Can we come up with like cell program or something that will put, I had also written down, I think I can bring back, I have written like 100 questions in there. And then you answer these questions and you fill in this blank, right? And then the Excel or something will create a report and they will say, okay, each question answer, and it'll, like ChatGPT almost. So it will give the answer, and then each done for each person, right? So each person fills in that, and then it'll say like a Twitter, Twitter, it'll limit the number of things you can put in there. You cannot put references. Okay, Gerd says, go to a page, this thing. You cannot do that. You go page 332 and refer to that picture. You cannot do that. You have to put, without references, you have to actually put the whatever is there in there. You know what I mean?
Yeah,
so
like
if there's an equation, you have to put the equation and explain that equation completely. Christian is saying that one person, what is his name? He says that how you should explain that equation. I agree with that. So suppose I say equation.
If you're talking about I know in one of your papers there not too long ago, or well, maybe it was a while back, you're talking about eigenvalues and stuff, and so I think you had the psi wave function. I mean, I can convert, from whatever to eigenvalues, and I can do all these conversions, but I have absolutely no reason to use eigenvalues. I know how to do it, sort of, but I have no reason to do it. I mean, maybe that's because I'm not using.
I would think eigen. I tried to translate to simpler physics. So eigen, I would think it's like a unique thing, in the sense that you can think of an umbrella. think of an umbrella. So you had a simple picture of an umbrella. You know how an umbrella works, right? So you have
umbrella,
something there. So you can think of that rotation like that. So there, then it has ribs that come from there, right?
Yeah.
From the central point. The connection. So eigen is like that thing, the middle that holds all the ribs together. The value of that. So suppose you remove all the ribs, what will happen to that? How do you describe that? Eigenvector is something like that. You know, a simple way. And then the ribs are like a cardinal thing. That.
Wait a second, though. You have an eigenvector is like that is a vector that's invariant under some transformation.
Yeah.
So let's say
invariant, right?
What?
Suppose I put umbrella down, umbrella up, you still get the same thing. Only the thing.
Yeah, but an eigenvector has like length and magnitude, so it's more like one of the ribs than it is the point. I suppose if you're talking about
eigenvector,
an eigenvalue, then is like a different thing. But then, yeah, I suppose it's more useful in general relativity where you.
It depends on what coordinates you
use. Let me speak. It's probably more useful in general relativity where you've like, you know, invariant like transformations, and you're interested in what stays invariant. But then you often hear of like eigenvalues in terms of the mass terms or something like that. So the mass terms are all on the diagonal. I don't know. Is any of this like stuff related to your work, or would that be?
Yeah, it is kind of. So one of the things I like to do, I think you have a good point there. We can come up with first question is, what's an eigenvector, and how do you conceptually? So we can break it down like that, and then you do what is invariance, and how does it connect with eigenvector? Things like that, you know.
Well, I suppose an important invariance in a transformation, maybe in special relativity, would be what the speed of light, you know.
Yeah,
it's going to be invariant. Then, what would be invariance in a transformation to do with general relativity, though? It wouldn't be the mass. It could be the mass, though. No, but I suppose that, you know, if you had. Maybe if you were stretching something like this way.
Ricci tensor.
Huh?
Ricci tensor going to zero, curvature.
Yeah, I don't really get the
curvature of space-time.
Who's this Ricci person anyway? I know who Riemann is, but who came up with the
Ricci tensor? It's a simplified Riemann thing. It's a specific case of Riemann.
Okay. Yeah. So, I mean, I'm basically using the Riemann kind of stuff, you know, but I just leave out all the complex standard forms and all of that. I'm just working in Cartesian coordinates because they make sense and they're easy. I mean, I can totally project into other, you know, into the complex plane, or I can project from the quaternions, whatever. There's no real need to do so, though. That's what I'm finding, and then so it'd be nice, like there's just actually I don't really think there's a need to connect my work to the Riemann sphere in order to connect to relativity. I would say that I'm just it seems like relativity is definitely in my model, but it's like not important. It's like, yeah, it's in there, but like it's the same way like all the particles are in the model, but they're like, yeah, they're just there. They don't really affect anything, like, in a sense. Like, well, the model does affect them, though. It can change the particles from one state to another, and there's certain relativistic effects that happen on large scales, which go into making the universe look like it expands, and but time is also slowing down as you go further out, so that creates some of the again more maybe more
the clock ticks more faster.
Yeah, you know the way apparently if you look at there's certain processes out in space that they know how long they take. Like let's say a supernova going off, and they know, well, that takes 21 days. But then the further out you go, it's taking like 100 days. So it seems like time is slowing down as further you go out. So my model can cope with that. But their model says, oh, that's happening because space is expanding.
Gravity. And also gravity is acting, right?
They're saying that that's happening because space is expanding. So, but that doesn't make any sense, because if space is expanding, then the light wavelength is getting longer, but the frequency is increasing to compensate for that. Yeah, for
keep
light
the speed of light constant.
Yeah, so we will just, when the light hits us, we won't see a time delay. We will see it happen in 21 days. But in my model, the light ray is constant on the hypersphere, and the metric is logarithmic up to the point at infinity. So when it's reprojected onto the tangent plane, it becomes stretched. But because the light is constant, it has to move. It moves faster across the same distance. The further out you go, it's moving faster across the same metric distance, and then it gets slower as you go in here. So if light is moving faster, then time either has to accelerate in order for us to read the same value of time, or it slows down. You know what I mean? It's because it can do both. You could like speed time up to match the faster rate of time.
So you say superluminar can reach superluminar, you say?
Well, no, I'm just saying, how do we let's say the light is moving faster. Yeah, it would be, yeah, like
suppose light is stretched. Suppose light is stretched. Will it move faster?
No, it wouldn't be well, it could be stretched. Yeah, it would. Well, yeah, maybe it's just stretching the light then. So, well, so these are things we'd have to work out, because I'm not you know, I'm looking at it one way. I think there's like hundreds of years of cosmology, and they're looking at it another way. I would probably defer to them, but I'm still like, all I can do is interpret the model as I see it,
yeah,
and hopefully get something right. You know, so it could be, yeah, I was thinking about that. But that would mean that the light would be stretched. But even so, right, if the light is constant on the hypersphere, it's going to travel that small distance on the hypersphere. Let's say that the metric's getting logarithmically smaller as it goes up to the top, yeah? And you were talking about this last time, I think, logarithmic time and nonlinear time. So imagine that, right? It's going up, and the metric gets smaller and smaller logarithmically until the point at infinity, or the North Pole, where it's like zero distance. And then if you were to project that onto the tangent plane, all of those lines now aren't getting tighter and tighter together. On the tangent plane, they're equally spaced apart. So if the light on the hypersphere is constant, and it's able to travel at a constant speed, then when it's projected onto the plane, now it's like, if it only took like a millisecond to get across between one of these metric things, it's only going to take a millisecond to cross this entire space here, which could be equivalent to, like, I don't know, trillion light years or something. So in order for the speed to be, you know, so that it doesn't travel superluminal, time has to slow down in order for it to appear that it's not traveling superluminal, but it actually is. But that could be all. You see, this is the problem with relativity that I have, because you could also say, well, time is speeding up out there then, just to catch up with the light, you know? So that would work as well. Or we could say, well, light isn't constant on the hypersphere. Light is only constant on the tangent plane and variable on the hypersphere, and that would change. So this is the problem, and there's, like, as far as I know, there's no way to prove which of these two things are the case. So we could just say, well, either is true, you know, back and forth. And then, so that'd be the kind of thing that'd be interesting to work out. Does it matter? Does it have an effect on the theory? So for instance, if we're saying that these quasars are happening slower the further they go out, well, then we know, okay, time slows down the further we are out. And then, but is there also a similar, does that have a consequence then to, is light constant on the hypersphere or on the plane? And then you could work that out. It would all just be logic based on observation from the universe. These are things that we have to do when we, hopefully when we get more time, when we take over the world.
Yeah. So one of the things I can think of is in the hypersphere, it's more like general relativity, a curvature, space-time, curvature of space-time, which is Ricci tensor, right? Whereas you project into the tangential, it's more like special relativity. So you have general relativity there, the hypersphere, and special relativity in the tangent state. If we do that, maybe we can get some answer. Like this is a Ricci tensor here, and then you have the special relativity by Lorentz transformation, whatever. On that.
Well, this is it. I mean, that's very similar to. You go back and watch the bit that myself and Gerd did while you were away.
Yeah, I will watch that. Yeah,
because we go into all of that using anti-de Sitter space. They talk about special relativities on the boundary and general relativities in the center of this de Sitter space cylinder. That's fine, and then you can go into complex mathematics of like Minkowski spacetime and whatever Ricci tensors if you want. But see, in my model, it's all very simple mathematics. I think I use about 6 equations or something to do the whole thing, and that's fine. Well, I mean, maybe 12 if you want to do the inverse as well. But it's all very simple mathematics. But you could make it as complicated as you want, but there would be no benefit, I don't think. Also, there's the issue that, they tried to do the de Sitter model of space where matter was dominant and forced curvature of space. But now we know that space is flat. So matter has no contribution or very little to the actual curvature of the universe. And so really when they say that, quantum mechanics is the physics of the very small and general relativity is the physics of the very big, that's not actually true anymore. It's been proven not true by the flat nature of the universe, by the fact that anti-de Sitter space is not a real theory, that inflation is not being proven, and so on and so forth. So relativity is fine. I accept it. Special relativity, I have no problem with it, but it's not a theory of the very large. It is, if anything, probably a theory of the mesoscale, like just where we are and up to like stars and stuff like that. I mean, you could extend it out to galaxies and clusters and whatnot, but in a very, like, you could just do that with Newtonian gravity as well. It's just gravity, it's no big deal. But then obviously quantum mechanics, theory of the very small, but I think the real theory or model that's going to explain it all is my model. I have to be very blunt and say that, but no. But what I'm trying to say is that the theory that will explain it all will unify the very big. Well, no, it'll unify the very small with its own model, which is of the very big, and then relativity will be just in the middle. But the point I'm trying to make is that my model is a model of the very big, like the biggest thing you can get, and it is also a model of the smallest things, and it also has special relativity implicit in it on a very small scale as well. So, which is, completely proven by previous mathematicians like Dirac and the Klein-Gordon equation and all that stuff. So, I believe. So, but the point I'm making, I did say that my model is the correct one, and I don't want to boast there, but no, I think it could have like some very, as Gerd said earlier, all models are wrong. So this could apply to mine as well, of course. So, but I just like the idea that if it is right, or what I should say is general relativity is not the theory of the very large, but that I believe that my model does have some explanatory power towards the very large and the very small, and that if there's going to be any model that is correct, is going to unify the very big with the very small, and that's what I think mine does. So in that sense, I think there's a good chance that my model is correct. But as I say, I'm not boasting, but that is my good feeling at this point. But it's still a good feeling because there's a lot of stuff to be proven, and actually, I wouldn't even call it a good feeling. I mean, just looking at it, it seems right. But as we go on and as we compare with the huge amount of experimental evidence they have, and if it starts contradicting, then we know it's not right. Okay, but it looks to be you have to go there, Rajan.
Yeah, I have to go. So only
Okay.
the one thing is one supporting thing, and we'll continue next week. Again, next week maybe 1 to 1, and I have another appointment. So 1 hour probably we can do, but maximum 1 hour, maybe half an hour, 1 hour. But the thing is that,
well, we can skip next week, you know, if necessary. But
half an hour. I don't like to skip.
Yeah. Okay.
Half an hour, 1 hour if possible.